Hello, a very good afternoon, good morning, and good evening to everyone from different places who have joined this conference and summit. Myself, Kalpesh, project manager from ZF and executive committee member from INCOSE, India chapter.
Hello everyone, I am Neha Tiwari, Systems Engineer at Boeing and Executive Committee member of INCOSE India chapter. On behalf of the organizing committee, I extend you all very warm welcome to the Model-Based Systems Engineering Summit 2022. So, International Council of Systems Engineer INCOSE India, Aeronautical Society of India Design Division, and IEEE Systems Council Bangalore Section Chapter jointly organized this MBSC Summit 2022. We sincerely thank our platinum sponsors, Collins Aerospace, gold sponsors, Capella and MapleSoft, silver sponsors, Honeywell Certification Training International, CTI, and CATFAM, and CIS for supporting event. This summit aims to bring together experts from multiple sectors such as aerospace, automotive, healthcare, etc., to share their research findings and expertise on the state of art in MBSC and its applications and how the different industries can benefit from its adoption. So, in the presence of all the eminent dignitaries that we have here and all the guests, let us begin this auspicious event with the traditional lamp lighting ceremony.
कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः.
Thank you. Let us now commence the summit by requesting Dr. Kota Hari Narayana, Science and Engineering Research Board Distinguished Fellow at CSIR, National Aerospace Laboratories, and Chairman of Aeronautical Society of India Design Division, also Padma Shri. We cannot introduce him, everybody knows him, to deliver the welcome address.
Good morning, good afternoon, good evening to all the people around. And we are very happy to be here. And whether you are in designing an aircraft or a helicopter or a rocket or an automobile or any one of the major subsystems, you are developing a system of systems and connected with each other. And the functioning of one system has a tremendous impact on the other systems. Each system and subsystem, they are designed, developed, and produced by a team of engineers, and they bring the whole thing to life. Helping all these equally important players collaboratively, effectively, is the purpose of systems engineering. And it has been doing this job quite well in the last few decades. But the system engineering is a multidisciplinary engineering approach which pulls together the complex systems across the whole life cycle. It is a robust approach which guides in design, development, production, maintenance, whole through the life cycle. Then the question that is asked is, if it is so, why do you need an updated approach to systems engineering when we have experience of dealing with the present approach, mostly based on documentation, and we have the experience of dealing with it for the last few decades? The point to be noted is that more and more functions are interconnected, consolidated, and controlled with significant amount of software. It becomes more complicated to monitor these thousands and sometimes even millions of interactions. And from a software perspective, as the complexity of aircraft or a system increases, the complex software also increases. When I, three and a half decades back, when we looked at the aircraft before we started designing our aircraft, light combat aircraft, perhaps the biggest software we had, maybe about 10,000 lines of code in an aircraft like Jaguar. And when the light combat aircraft flew for the first time, we had 1 million lines of code. And today it has 5 million lines of code. And this is leading to the next aircraft we are resuming, it will have about 15 million lines of code. So with so much of code and complexity, you need tools that can move quickly as you integrate software with hardware, with models, tools, and all those things. So it is also nowadays when the system, these complex systems are operating, the operating environment also has become complex. If I'm operating an unmanned air vehicle in a civil space, it has to meet tremendous amount of limitations, and the software must be able to recognize those things, recognize and work accordingly. And if it is a fighter aircraft or a transport aircraft, if it is then it is a net-centric warfare or net-centric civil system, and it must work in all these kind of scenarios. And that would mean we need to now develop aircraft, its software, hardware, validate, verify millions of lines of code, and ensure what you call the system works correctly and important, safely. Just as the tasks and technologies have become complex, the regulations also have become complex. An aircraft today, a civil aircraft, has to meet not only the safety requirement, which are increasing day by day, but also the environmental requirement, noise requirement, and many, many other requirements, which makes the job a lot more complex. And with all these kind of complexity increase, software increase, electronics increase, and all, the document-based systems engineering needs to be changed, and we need what you call a better system, and that is what we have to look at, a model-based systems engineering. Let me give you a small example where most of us have dealt with CAD engineers. With CAD, I'm doing a component and putting components together. I'm making a system or a subsystem and putting everything together. I have a what you call a digital prototype, a digital mock-up. But this digital mock-up doesn't still represent the aircraft functioning, nor it represents software, nor it represents its interfaces. So that is where we feel that a digital environment is required. Fortunately, this is a digital age with more powerful digital capability, digital twin, and the digital thread brings all these things together. So this is the digital innovation of system engineering to march forward. And some of the tools like SysML and all have now come to a fairly mature stage, and they are helping us to do a better job. So it looks to be that model-based system engineering with these tools, with the requirements, becomes an absolute necessary if we have to design a product well in time with safety and with performance that we are looking at. So MBSE enhances program execution by defining the system using modeling to continue to define product requirements and architecture. It enables design using multidisciplinary approach, and it can test virtually before you build, and it promotes usability, modularity. It manages integration across the supply chain and keep the tab on key performance indicator throughout the whole process. And it does many, 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 many things. It's so important now in the environment where we are in the 21st century. The MBSE is a vital thing, and all of us must learn, must master, and add to whatever we have learned in the systems engineering. So that is what I feel these 2 days you will learn from the experts, from practitioners, and I look forward to all of us gain enriched by this 2-day lecture. Thank you very much. Thank you.
Thank you, Dr. Kota. We are honored for you to be. We are honored you being in this summit. Thanks for your presence. So before we start with our summit, I would like to share some instructions with everyone. In case if you get stuck and if you need any technical support, you can always go to May I Help You desk, and there is a live chat support provided where all the concerns will be addressed. We also have a Ask Question tab. If you can check over here, all your queries can be addressed. You need to connect from there. And we have in COSE SEP a mock exam planned tomorrow morning. So this exam can be taken from the tab shown over here. The agenda for the summit for today is we'll be having 4 talks and we'll be having a panel discussion along with sponsors video. Now we are starting with our summit. Over to you, Neha.
Thank you, Kalpesh. So can we move to the another slide? Okay. So coming to the talk first, I would like to invite Dr. Sukanta Bhatt, Masters and PhD from IIT Kharagpur. He has 30 plus years of experience spanning academics. Welcome, Dr. Sukanta Bhatt.
Thank you. Yeah. Shall I share my screen now?
Yes, sir.
Sure.
Okay. So let me know when you can see my screen. Is it visible?
It is not up yet, sir.
Okay, share.
Oh, sharing is enabled, right?
Okay.
Yeah, it's coming up.
Coming
Yes,
up.
sir.
We can,
Able to see.
yeah.
Okay. Shall we start now or?
Yes.
You can get into the presentation mode. Yes,
Sure.
thank you.
Good afternoon, good evening, all the participants. I cannot see how many people are there. You have some idea, Neha?
So right now we have about 70, 80 people. And
Okay,
we are looking forward to
good.
more joining.
So thanks, Professor Kota, for the introduction. So that session really makes my session easier. So thank you very much. So we are going to have a lot of stories here. So there is not really much technical content, but let's discuss and find out what we are and how we go forward. So as I see this system engineering during First World War, a little after that, I saw that operation research first started, right? And that is where a lot of optimization, but linear programming and all those things happened. And then slowly cybernetics started, where more of controls and feedback. And then where during Second World War, about 1940s, we saw first time, as you see in the Bell Laboratories in the around 1940s, where you saw the system engineering as a discipline started appearing, right? So it's as you see that it is a transdisciplinary and integrative approach. It's a very, very two important words here. To enable the successful realization, use and retirement of engineered systems using system principles, concepts, scientific, technological and management tools, right? So a lot of stuff as part of system engineering, and we do that most of the time. But very important thing I learned when I was deep diving into that is system engineering is not like electrical engineering, mechanical engineering or software engineering. It is engineering a system. That is the most important aspect of system engineering. We are here, you can engineer anything, right? So it is engineering something, a difficult problem or a project that you have to do. Say engineering a system. So that is the right way to put to get the right perspective. So this is the action of working artfully to bring something about, right? Because that's the goal or objective when you do a project, to bring something about. Pay attention to this. I will also come back to this particularly 3 words later, but it engineering something, right? That is the key thing. The term system engineering dates back to Bell Lab in 1940s, and Department of Defense entered the world of system engineering in late 1940s with the initial development of missiles and missile defense systems. So warfare is most of the time were triggered system engineering because they were pretty complex and big and very, very expensive as well. So what do system engineers do? So since they are at the heart of creating successful new systems, right? When we are system engineers, we do something new, something did not exist or something has to be enhanced. And that is where some of us, we are all engineers, and some of us start playing the role of system engineers, right? Creating something successful and new in the system. They are responsible for the system concept, right? Very, very important. What is a system concept? Most of the time, yeah, in our education, we do not, it's not being much taught because it's monodiscipline is what we all graduate. But then when you go to the real life world, we have to get into a system, right? So system is, in this case, say what is the purpose of whatever we are doing and what is the goal and what is the expectation from the customers, right? So system concept, then of course the architecture and design. They analyze and manage complexity and risk. Very, very two critical words. What we do nowadays or for many, many decades, the projects what we do are pretty complex. And all complex projects will have risk. So how do you analyze and manage complexity and the risk? Very key aspect of system engineering and system thinking. They decide how to measure where are the systems actually works as intended. They are responsible for a myriad of other facets of system creation, right? You will see that that person is like a jack of many, many things, also has to be expert of many things. So system engineering is the discipline that makes their success possible, but then you also need the tools, techniques, methods, knowledge, standard, principles, and concepts. I landed up in healthcare industry and last more than for 2 decades. And I can really relate, I mean, tools, techniques, methods, for knowledge, possibly most of us are aware. But when it's a domain specific and it's healthcare, standards plays such a significant role. And many times I have seen in startups, they make a big mistake in meddev space particularly. They think the standards are design verification. So that's the biggest mistake people do. Standards are design input, not design verification. Design verification has to happen, but primarily that's a design input, right? And the principles and the concepts. The launch of system successfully can invariably be traced to innovative and effective system engineering. System engineering very much, but pay attention to the word that innovative, right? As a human being, we are innovative and creative, right? But many times in the pressure or the load of the engineering or system, sometimes we do not pay sufficient attention to our innovative and creative skills. But that's also a very important aspect of system engineering when you do a big system projects. So these are other aspects is what system engineering do. Possibly some of them already you might have seen today, but quickly to recollect, manage complexity and reduce your risk, right? That's what we saw. Because bigger projects, system projects are complex. There are many stakeholders and not very easy to understand. And there are multiple risks are there. So we have to manage complexity. Maybe that's why we do a decomposition and then reduce your risk. Now look at this middle box. No, the failures that happens is so big when systems engineering is not done and you start ad hoc or just a monodiscipline. Over 1/3 of all projects fail. 1/3. Over 2/3 will not achieve their goals. It's as good as a fail because you put that and it doesn't meet customer expectation. It's also a failure. 2/3. Failure is usually obvious only when the project is overdue or over budget, right? And that is a chronic thing you would have seen in a complex projects. the project overshoot in the cost as well as schedule. But decisions and plans made earlier in the project can reduce your risk and sometimes dramatically. So when you do systematically and apply system engineering and other methodology, then these are the risks we can significantly reduce. Still some risks will be there, but that should be manageable. So this is a very important thing. You will possibly, those of you who have a little complex project, all of you would have experienced it. Then very important, don't rely on luck, use system engineering, right? So many times when you are really struck, we tell, okay, we will see on the way how to manage it. Let's start, right? And that's a very, very risky thing when you deal with complex systems. So better start using more systematically and apply the methods and tools of system engineering. Then what is system engineering? Possibly all you know. So build the right transportation system, build the system right. System engineering links the economic benefits of the new transportation system and is a high level design down to the subsystem requirements across the whole system life cycle. Pay attention, high level design down to the subsystems, because that is the decomposition, right? And that is where requirements also decompose across the whole system's life cycle. I'm very, very attention to the life cycle. And I've seen at least the medical device and many other devices, even automotive, they live for decades, right? And we design, is it going to run for a decade or 50, more than a decade? That's also a design consideration in system engineering we need to pay. Because as you know, those who are hardware engineers, in 10 years, possibly 3 times obsolescence will happen, right? In software, yes, the OS will change every 2 years, right? So many things does not work when these changes happen. And you see a lot of problems and factory manufacturing stop and all those problems comes. So it's a really, really n number of elements we need to pay attention when you handle a complex projects. So here, 7 steps to success, right? The first step is understand the problem, right? Of course, everyone tells what's the big deal, but those who have gone through a complex project, we see how many times we make an assumption and then see, hey, something really did not work, right? That's the reason why it is the first one, understand the problem. And I will discuss little later why as a human being, we have a challenge to understand the problem in its entirety, okay? But this is a very, very key thing. Then investigate alternative solutions, right? Because as human being, we will see that, hey, we want to solve something quick. And whatever comes first, we will go ahead with that. But many times we know the first few ideas are not always the best because they are tried and tested. And many times is not the super idea. And that is why it tells, hey, look for alternative solutions. At least consider that. So that halfway through, if you reach a bottleneck, then at least we tell, hey, we had also thought of solution 2 and solution 3. Let's go back and evaluate that. Otherwise, there will be a lot of panic and chaos in the projects. Define and agree upon the system architecture, right? Because these systems are going to stay for a long, long time. And as you discuss, hardware and software both will change. What should be the architecture we should choose so that it will sustain and live for a very long time? Next is agree and manage the requirements, right? Easier said than done. When there are multiple stakeholders, each one have their own goals and objectives. And in many times, these goals and objectives conflict with each other. How do you, in that situation, agree and manage requirements, right? So we will discuss a little bit. There are some tools and methods also in system thinking to address particularly these aspects. Agree and manage on interfaces because we decompose and therefore there will be interfaces. And that is what is important, particularly where you compose it back, when you do the integration, right? If the interfaces are defined well and agreed and we have managed it, then we will see when you decompose it, components will come, you will a module will come, you build an assembly and assembly is put together, build a system, you will have a good story there. But in my experience, lot of trouble comes in system integration in projects. Prepare the test and support systems, right? So doesn't matter what you do, we need to verify and validate, right? And we have different operational system, environment, users, so many aspects are there, right? So those are also things we need to specify very early and define the strategy there. Otherwise, lot of pain at the last phase and projects will slip. And track progress against the plan. Of course, this do that because project management is one of the focus area here. And just to mention, PMBOK 7.0 has included systems thinking as one of the tools and methods going forward. So these are the 7 steps, which is the knowledge with lot of experience from years, which has come very nicely captured here. So here we see now system principle and concepts are the way that system thinking and systems science has built in for the system engineering. So as you see that system thinking is part of system science. Okay, system science is evolving for possibly 60, 70 years. And those methods and principles enriching system engineering. So they are not really completely different. They work together and enrich each other. So what are the principles comes from system thinking to system engineering? Is holistic thinking. Look for the big picture, right? Everyone tells, hey, look and think what is end to end, right? Separation of concerns, right? So how do you decompose what is who bothers about what, right? And how do you put together? And a real life is very, very complex. Therefore, we do abstraction because then it's much easier to manage it, right? And then modularity, because when you do separation of concern, we do the decomposition. Therefore, modularity comes into play. And then encapsulations, right? And the level of abstraction we can do, so you can manage easily. Causal loop diagram, because when you design, you will see there are cause and effects, right? So when you do a simple causal loop, you will see that we do a root cause analysis, but when you do that as a loop, then you will see there will be reinforcing loops. Sometimes you will discover, sometimes you will see balancing loops, and these loops have a story, is what is happening, why something is happening or not happening the way it is supposed to happen. And you will find very good leverage points when you do this diagramming. And system mapping is a very, very useful tool. Basically what it tells is, don't take the whole elephant, right? Take a piece of the problem and put it visually and clearly define, hey, what is the problem? What is its boundary? What is the context of the problem? And what are the things outside the problem? Very, very important. Otherwise you will confuse and then do a wrong choices and design, right? System archetypes are typically the structures or common fault patterns or things that does not work, or you see some people keep on doing that. So those are the things called archetypes, and systems theory that is very much used, right? So these are the things from your system engineering tool org only. It is all available and I'm pulling out from there. Now, are the problems you are dealing simple or complex, right? Possibly most of you tell that, hey, the problem we face are really complex. Are there multiple actors with different goals, right? Unless a very simple problem where a monodiscipline, most of the projects we handle today are having multiple actors, and therefore, for example, starts with upstream marketing, right, and service. They will have their target and goal based on the competition, right? So that is one factor that comes. Then comes your design team, right? And then you have marketing, there is regulatory, right? Then operations, supply chain, supplier quality, so many aspects and actors come into this. And each of them have a little different goal, though we are trying to achieve the same project. So this is one thing I want to bring to everybody's notice. It's called Barriers to Learning. It is from the book called Business Dynamics by John Stearman from MIT. So he brought out a couple of common things that we all do or mistake. Most of us go for short-term views or quick solutions, right? It's a very human tendency because our brain has evolved in a very reactive way. So all of us by natural tendency will go for short-term goals. Then a very important concept is fundamental attribution error. Here it tells we do project and something goes wrong. We will see our instinct is always who is at fault, not what is at fault, right? And this is always a low leverage point and it does not help. We should sit down and look, hey, how we are working, what is the process and why this happened, rather than telling, okay, who made the mistake, right? So this is called fundamental attribution error. The third one is called bounded rationality. Dr. Simon got a Nobel Prize for this. Here, what it tells is our rationality is limited when we make decisions. Okay, we are selective from the variables that, because in real life, the variables are many, and we choose a few that we are comfortable, and based on that, we make decisions. So this keeps on, they have done many psychological experiments, and human beings keep on doing again and again. If you all also reflect that in some big decisions we have taken, we would have landed up in this situation. The fourth thing is from cognitive psychology, it comes, is the variability a human brain can handle at a point of time is 7 plus or minus 2. So they have also done, particularly Peter Chuckland, I have seen many experiments they have done, is beyond that we will blur out or we will ignore it, and that is where our limitation comes. And of course, the last two, we all know, if you are our opinion or our idea, we are very confident. Oh, yeah, very much, I know it will work, right? And we also wishful thinking. We'll think, okay, somehow it will work it out, right? But in real life, many times it doesn't work it out. So these are our, as a human being, our human brain, our challenges, and we deal with complex projects, right? So I will just play. Are you able to hear the audio?
No, sir. No.
Okay, just one sec. What do I have to do for audio? Anybody can help? Okay.
So you'll have to stop sharing and share audio.
Oh yeah, while starting something I have
Yes.
to do, is it? Okay. So stop share. Screen share. Where is the audio here?
At the bottom, if you see
share
there is a
sound.
share sound.
Stop. Share sound. Optimize video clip. I don't know. Should do. All right. So that should be okay. Let's see now it works.
Systems thinking.
Are you able to
A
hear
way to
now?
maximize program effectiveness. Systems thinking.
Hello.
Maybe you've heard of it or
Yes, sir,
doing
we
it,
can hear.
or you've heard
Okay.
that you
Yes,
should
sir.
be doing it. What is it, and what does it mean for the senior manager? Let's start by looking at what a system is. A system is any kind of entity that is made up of parts that interact. Together, these parts and their interconnections create a whole, which in turn produces some kind of result. Using a systems perspective is important because it helps us to better understand what helps or hinders the success of health interventions. Here's an example. Meet Suzanne. Suzanne is a senior manager in a large regional health organization. The high rate of obesity is an issue in her community, and she's been mandated to address this problem. Her first instinct is to develop a program to get more people active. But what is realistic to expect from this approach? Systems thinkers believe that viewing a program like this, apart, in isolation of the larger system within which it operates, the whole, tends to ignore other aspects that might influence its potential for impact. Why? Research tells us that obesity is the result of a combination of many physiological, psychological, social, environmental, and economic factors that all interact with one another. For example, at the individual level, there are issues such as human physiology, exercise habits, food choices, and one's occupation. But beyond the individual, there are other factors at play, such as the local built environment, quick and easy access to junk food, and larger food industry practices, such as trends in portion sizes, sugar, and fat content. The interaction of all these influences make obesity the product of what we call a complex system. If Suzanne were to use a systems approach, she would realize that relying on simple linear cause and effect solutions for one program would ignore those interactions and likely fail. While Suzanne's staff at the program level have a tendency to think only within the boundaries of their program, senior managers and planners like Suzanne are in a unique position to do what systems thinkers call zooming out. Zooming out considers how other aspects outside of a program's traditional boundaries, both within the organization and beyond, might influence the success of the program. By zooming out and looking at the influence of other interventions, policies, structures, patterns, and norms in the broader system, Suzanne is better able to strategically consider other values and perspectives and the interrelationships among each that may impact obesity rates in her community. In doing so, she can identify more powerful leverage points outside of the program that have the potential to facilitate and support changes in obesity. Leverage points are places within the system that can be tweaked in a way that supports greater impact. For example, are there actions Suzanne and her team might take that could increase the community's access to opportunities for physical activity? While some leverage points are within Suzanne's capacity to change, others will be beyond her control. However, it will still be useful to be aware of these as she plans for the program. Adopting a systems view won't change the boundaries of this program, but it will expand the boundaries of the evaluation. By recognizing the importance of the different perspectives and values of those outside the program and the interrelationships throughout the system, Suzanne can ensure that the evaluation is framed in a way that captures the key boundaries, diverse perspectives, and interrelationships that serve as important leverage points in the system. Of course, Suzanne's budget won't permit an evaluation of the entire system, but she can ensure that any evaluation she commissions will provide her with more strategic direction on how to effectively address obesity within her community.
So if you reflect the previous example, right, that's a pretty complex problem and whole world is struggling. But if you saw how the problem is first analyzed, expanding the boundary or having a balcony view, we see the problem in a very different context, and that helps us to discover high leverage points, right? So we all are system thinkers, we all are system engineers, and they are all pretty well related, because most of us would have heard, hey, look at the big picture, look at the end-to-end, think global. So that is the key concept. There are 6 key concepts in systems thinking. So first is the interconnectedness, right? We all know whatever system you do, there are elements, there are parts, they are connected, right? It's a very natural, everywhere, every system, even our human body also like that. Then this is very important. We are trained for getting to the smallest element, divide and conquer. But in system thinking, we try to look at the whole, right? That's also in system engineering, we saw, hey, look at the big picture. So that is what is called synthesis. And the third point is emergence. So this is very simple concept. For example, when you do a project, we saw that there is a goal by why you are doing that, right? So that goal or purpose is nothing but emergence, right? For example, you work for a car or an automotive, right? So many components, so many electrical, mechanical, right? So many software, hardware, everything there. But the end, what is that thing which is bigger than some of the parts coming together? Right? Look at the comfort you have going in any kind of road, right? You can climb a hill, you can go down slope, you can speed, you can go to the jungle, right? So that is much bigger than any of the wires or hardware or mechanical or software there. So that is what is called emergence property. For example, human beings, right? We are fundamentally built up of proteins, but look at the kind of creativity, kind of power, kind of energy a human being can display. And that you cannot tell because of this cell or this organ, right? It doesn't belong to heart or brain. All together, such a fantastic thing happens from a system. So those kind of properties are called emergence properties, right? And feedback loops, as you discussed, when you do a causal loop, you do as a loop, as a feedback process, we will discover, and there are in the universe only 2 types of feedback loops, right? Reinforcing and balancing. Balancing feedback loops are called goal seeking. For example, our body temperature, 98.4 is a goal seeking, right? What doesn't matter what we do, the body will try to take it there, right? So those are similarly our lot of blood tests. What you do, most of them are balancing loop seeking towards a goal. Whereas there are also reinforcing, which will keep on increasing. For example, sometimes you will see stock market. Right,
Dr. Sukanta sir, I'm sorry to interrupt you. We only have 4 minutes left.
Sure.
So, okay. Thank you.
Right. So that is where we see the reinforcing balancing loop. Cause and effect, that is very common known. And system mapping, as I discussed, we see interconnectedness, relation, and action. 3 things I want to draw your attention when you do a causal loop, right? Every system will have delay. Delay are inherent in any system, okay? So, but when you do this causal loop and when you see, hey, when the effect will come, if you start questioning, hey, when it is going to happen, you will discover the delay in the system much before it is happening. Otherwise, this is a pain for a lot of people. Second instance is called non-linear because our brain is triggered for linear thinking. But a lot of time in natural, the real system, the response will be non-linear. Cause and effect is not linearly related most of the time. So think through that. Hey, is this response linear or non-linear? And the third thing is where the response will happen, right? So that is sometimes very, very unknown. So when you do this kind of thinking, very early you'll be able to discover, oh, this response might happen this. For example, I made a look at the COVID and the supply chain disruption. Who thought that will going to happen, right? That is a very good example of where it is going to happen, right? And then right side, you see something a famous called iceberg model. You all know this. When you do a daily management, right? You look at the key events and you draw a graph, which is nothing but the behavior over time, right? In system theory, what is told is all the behavior under that there is structure. Structure is responsible for all the behavior, as you saw in the diabetic example. Unless you would have done that analysis, you would have treated the behavior, therefore the actual problem will not solve. So whenever we deal with complex problem, if you do this analysis, you will discover high leverage points, and those are elements which are coming from the structure. And below that is very, very key thing is our thoughts and beliefs, right? That is many times will disable or enable us, but most of them it is not visible. But if you do a workshop and start doing that and put visually, we'll be able to see that, hey, I was thinking like that versus you thought like that, and early alignment can happen and a lot of pain can be reduced. So yes, so now I am in the QA.
Yes, so we have few questions for you, Sukanta Bhatt sir. So how do we manage the balance innovation and standards, especially when they are constraints during the early phase of product development, considering constant upfront can limit innovation?
Yeah, so see, that's a fact of life for most of us, right? So what I do, I conduct a lot of workshops for real projects. What I discover is we do something called rich picture, rich graphs. Okay, it's a freehand graph picture. All the cross-function team we go and whole corridor or the room we put out the flip charts and start putting each of us how we are looking at it. Okay, and what do we see are the bottlenecks. So that is the place where very easily with a half a day or one day you will be able to identify, hey, which are the points we have agreement, which are the points we do not have disagreement, and then we can go to stage 2. Hey, these are the having disagreement. Let's look at, hey, what's the benefit to the end to the business and to the customer. So if you focus on at the customer and the value, it's much easy to be agreement and alignment. Then otherwise we will fight our own battles.
Okay. Thank you so much, sir.
Yeah. Any other question, any other thought or remark?
So we have few more questions. Maybe I'll post that questions in our website. You can answer after that. Sir.
Sure. If anyone has right now, I can answer. Otherwise, I can as well do that.
Thank you very much,
I
sir.
think they have a time thing, so we just manage in time. Thank you
Yes.
very much, all of you. It's a very quick intro, but as I repeat, we all are system engineers and we all are system thinkers, right? Only we are not very consciously aware. Now from today onwards, you are also system thinkers. That's why I declare. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir. I want to thank you for the insightful talk on the systems thinking for MBSC. Thank you very much.
Okay, thank you.
Can we have the next slide, Kalpesh?
Sure.
Okay, coming to the talk 2, I would like to invite Mr. Niranjan M., General Manager Technical at Bosch Global Software Technologies Private Limited. He has 25 plus years of rich experience in research and development, technical services, innovation, new product development, and systems engineering. We welcome you, Mr. Niranjan.
Thank you very much. Can I share my screen?
Yes, sure.
So it says I cannot share while others are sharing.
Yeah, okay.
So please give a try now.
Yeah. Can you see my screen now?
Yes, sir.
Okay, full screen, not.
Yeah, we can.
Okay. Thank you very much. So, good evening. My name is Niranjan. So, I am representing Bosch, and I would like to give. Can you hear me clearly?
Yes, sir. Clear.
Okay. So, I would like to give a practitioner's perspective today. So, I will not be talking about INCOSE and systems engineering concepts as such. So, where I come from, so I represent Bosch. As you know, Bosch has 130 years of history, and we are working towards improving the quality of people's life. So we are majorly into several things. Most of us work for mobility solutions, that is automotive and other solutions. And we also have industrial technology, we have energy and building technology and consumer goods. So whom I represent today, we are, a big company in India itself. I represent Bosch Global Software Technologies. So we are actually delivering most of the services to Big Bosch. So whether it is connected products, embedded technologies, data sciences, AI, in automotive, healthcare, manufacturing. So we are into different things. So now I would like to go about today's agenda. I will be talking why systems engineering at this point in Bosch, even though we have such a big history of engineering. So we are a technology company. And why MBSC in Bosch now, and why what is the framework we have at Bosch, what we are following, and my approach or our approach. So I am almost coaching most of the systems engineers here in India, and what are our focus areas and challenges. So I will be talking about these four aspects. So now let's just look at why systems engineering at Bosch. So we have actually three major challenges. One is the technology is changing very fast. As you know, VUCA world and complexity is coming from external world, as well as internally we have huge complexity because Bosch is spread worldwide and we have development centers all over the world. How are we connecting each other to develop a product? So that itself causes huge complexity. So whether it is VUCA world or technology or complexity, we have complexity coming up in automotive world. For example, we are moving towards automated driving, and this ADAS is bringing huge complexity to us. And if I take some of the aspects, we are involved in connectivity enabled products. We intend to become an AIoT company, artificial intelligence and IoT, a mix of artificial intelligence and IoT. We are serving markets worldwide. You know, there are needs coming up with the developed market. There are needs coming up with emerging markets. Systems engineering is very crucial for us because more and more new competitors are coming to us, coming to the development world where we are in, and more complex products. And we have our own goal that how to create an opportunity where our engineers, whether they are working in hardware, system, software, mechanical, how can we work together to find an optimum solution? So if you see complexity at Bosch, do you think complexity was not there earlier? It was simple. You take example of Beetle. We were having complete clarity on the left side, what I am showing. We had powertrain, we had chassis, we had a cab and other things, but mutual influence of components was visible. Whereas now we are into a car with more than 60 ECUs, 100 million lines of code, connectivity via distributed systems. So how can I understand the behavior of different systems working together? This is not possible without systems engineering. So we are convinced with this. And what are we doing? We have built a framework for us, of course, based on INCOSE. We want to have a cross-domain system design, and we want to manage the interdisciplinary work during product development with models, model-based systems engineering, starting from stakeholder needs until implementation and system integration and delivery to customer. So we are also working towards retirement of the product, until retirement of the product. So how are we doing it? So if I take our actual framework, I want to give an example of our framework in automotive application. We have systems engineering starting from eliciting the requirements from stakeholders, doing proper requirements engineering. We build a system architecture on the left side of the V. But what are we struggling with? Then we need to have a change request, stakeholder requests flowing into software engineering. Software requirements should get requirements from the system, and software architecture design is influenced by the system. In the same way for hardware engineering, electronic hardware engineering, for our ECUs, in the same way for mechanical engineering. So this is how we have built our framework, starting from system and flowing through software, hardware, and mechanical engineering. How are we doing it? I would like to take a simple example of ESP. ESP, you know, if I take, it has an electronic control unit, it has a vacuum booster, it has hydraulic lines, it has sensors, it has wheel speed sensor, steering angle sensor, yaw sensor. So it's a culmination of hydraulics in the brakes, it's a culmination of sensors, ECUs, and ECU should also talk to other ECUs. So how am I going to do this? For this, I will use the, we already started using MBSE framework, and we want to have a common engineering model. So you start from chassis and powertrain system and other systems, starting from there until the ECU. We want to have a fundamental asset of the core model, and we have adopted the SPES model, SPES 2020. This was, as you know, University of Aachen have come with this, where we talk about viewpoints. Viewpoints are very important for us in our engineering, because the problem statement should be expressed in requirements viewpoint and functional viewpoint, and then we want to move towards logical viewpoint and technical viewpoint for the solution. So there we can find solution for system, hardware, and software components. So this is how we want to enable a seamless model-based systems engineering integration in our product development. So how are we doing it? If I take PLM, product lifecycle management, if we want to integrate PLM also in MBSE, how do we do it? In the V model, we want to start at requirement stage, where interlinking information between PLM and MBSE, and then I want to integrate MBSE and PLM in system architecture level, and then moving towards cross-discipline change management, variant management at implementation stage, and correct version of the test should be used. You know, PLM advantage of working with PLM is it can give single source of data for us. And at the end, the correct test bench data, I want to check the traceability with the requirements. So this can be achieved with by integrating PLM in model-based systems engineering. So it's a good culmination, I would say. And our approach, we want to, what is our approach in Bosch? We want to understand the external drivers, as I said earlier, and our internal complexity within the organization. It is not possible if I don't understand our own complexity within our organization to conquer systems engineering. And second is need of systems engineering wherever it is very much required. Bosch is having many product lines, as you may know. So where it is required, how we want to implement, especially in connected products, and we want to we have built already a strategy for system integration, verification, and validation of components. And lastly, we want to assess the current roles. See, roles and transformation of roles is also important in an organization, because systems engineering practices can be taken to a defined level by defining clarity for each role. So with this, I want to say, why do we need to change something? Because if I look back our old methodology, I would call it as A model, and now we are moving towards a V model. So if you see system development, if I move to mechanics development, hardware development, within that low-level software as well as software development, these are different islands. There was no link here. The link was very weak. So we want to establish system development. First of all, change the mindset, increasing system complexity, which is going on. But how to conquer this system complexity? Very consistent requirements engineering, traceability across the V model, and have a very good interdisciplinary collaboration between hardware, software, and mechanics. So this is what we are trying to do. And I want to bring our focus areas. The third method or third topic I want to talk is focus areas, where I want to talk requirements engineering is one of our major focus. Without proper requirements engineering, we cannot achieve systems engineering goals. We realize this actually, and then build a good software architecture by considering the real drivers. The drivers which drivers I need to consider for software architecture. This is very important. Which stakeholder is important, which stakeholder is not important. Then look at software maintenance. When we deliver the products to the field, I should think about the software which I am going to maintain. I may do several updates, because as you know, software development cannot be done with 0 bugs, as you know. So then how can I achieve this? Lastly, about traceability, which will take us to achieve ASPICE also, as you know. And the most important thing, I've been talking about interdisciplinary collaboration between hardware, software, and mechanical. So what are the challenges? I want to talk the challenges mainly the mindset. This is very important. So that's why we are bringing this change in mindset both at leadership level as well as engineers level. So it's as you know, this picture of requirements engineering, how the requirements are defined by customer, and at the end what we deliver to the customer. These things, right? So this is another thing which we want to overcome. And mostly, if I talk the left branch of the tree, the people who are working here does not know what is going on the right branch of the tree. So this mindset topic we want to conquer. And secondly, most important thing, we are working in model-based systems engineering with, if I take complete product development area, starting from sales and PRM and project manager, design people, software engineer, everybody is using different tools and different ways of applications, different ways of storage. For example, if you look at many salespeople, they may be working with an Excel sheet, and a PRM guy also may be working with an Excel sheet. Then the project manager moves to doors, for example. Then the software engineer may use a MATLAB, A simulation engineer may be using a different tool. How am I going to do this? This is the most difficult thing which we are trying to overcome. What I want is the MBSC which look like a database, consistent data used by the models with single source of truth. Of course, this is not possible in one go, but we are trying to build step by step in each product line. Whenever we are going to the next product upgradation, we want to do this. That is the single source of truth, so that there is a seamless interaction between all the people throughout the product development life cycle. And if there is a small change in the requirement, how can I take it very fast to design, simulation, and software engineering? So this is what we want to achieve. And in the same way, what I was talking today, most of the things which we have in many projects is document based, whether it is requirements, testing, security, safety, verification, and validation. So each engineering task creates a new copy of a part, and product description is inconsistent, lot of duplication of work, and there is a lot of misunderstanding. But we want to have a common engineering model. So this is the same depiction what I want to give from the last slide. We want to reduce view for each engineering task, reuse information wherever it is possible, and very consistent product description and common understanding of the model. So this is what we have been trying to achieve. I want to take an example of automotive application. So if I take an automotive application, we get 1,000 to 10,000 requirements in one system. Okay, you take a Mercedes or you take an Audi car. Then if I derive, there could be 5 to 10 user functions in each one. Then if I take this one user function, again will have 5 to 10 system functions. This is almost, I am going towards from problem statement to functions, and that means towards solution statement. Then if I go to solution, there can be 5 to 10 solution elements for each user function, and each system function there can be 5 to 10 solution elements. If I go further deeper, I want to take you further deeper, there can be 4 to 10 interfaces per solution element. How am I going to do this? This is huge. And if I take each system generates 100 to 500 artifacts, I will end up with 100,000 artifacts. Can I deal with 100,000 artifacts for a modern car application? I'm talking one requirement, say for example, a powertrain control ECU or any other ECU. So this is going to be very difficult. So this is the example I wanted to give you, how complex it is. And another complexity which we have is understanding system exists at different levels. The left one, as you know, in Inkose, the right one, if I take an example of e-vehicle, starting from e-charging to complete vehicle level, going to e-drive and then electromotor, software, hardware at different levels. There are 3 challenges. One, I can treat vehicle itself as a system. Second, my ECU itself can be a system. And further, the system exists at different levels, and our engineers should understand, am I working at this level? Am I working at this level? Or am I working at this level? This is very important. So this, if people starts realizing in any organization, especially in our organization, we are bringing this in a very focused way. Because, for example, this development may be taking up in Germany or Japan. This electromotor development may be taking up in India. And we may be doing function group, ECU software, ECU hardware. How am I going to have this kind of interdisciplinary approach across systems engineers and software and hardware engineers? This is possible only by understanding the levels and the views, as I explained earlier. So if I take cross work product traceability traceability is most important, because tracing relationship between different artifacts during development process is very important from a ASPICE point of view also. If we can consistently do model-based systems engineering, starting from requirement engineering until verification and validation, I can easily meet the ASPICE levels. You can take level 2 or level 3. This is possible. And I want to bring another challenge which we have. For example, if I take vehicle computing, vehicle computing, if I take y-axis from vehicle technology to mobility life cycle, we are working in a vehicle computer, with a vehicle computer level and vehicle cloud computing. So here you can see there is a vehicle computer available, which is interacting with cross-domain ECUs, again interacting with other many ECUs. So this can be one, and also linked to the cloud. The next level, there will be car-to-car communication. There will be car-to-infrastructure communication. There will be car-to-cloud communication. So how am I going to do cross-vehicle computing? Further, it is going to be, if I take the vehicle level to smart infrastructure level to smart city level, we are working already. How can I have personalized mobility for last mile connectivity through a smartphone? That is vehicle to infrastructure. Within vehicle, you have so much complexity. Vehicle to infrastructure, vehicle to cloud. So this is going to be very difficult. So to sum it up, how am I going to deal with models in model-based systems engineering is, I want to understand model complexity. See, if I take effort as x-axis and in y-axis model complexity, when I start a project with models and model-based systems engineering, their model complexity will keep on increasing. At some stage, my experts will find a solution. Then most of the mindset of engineers is to stop here. Further, I don't need to do, but we want to change this mindset. This is only building up the knowledge, but how this model can be used by other teams, by subsequent teams who are working on the upgradation of the products. This we call benefits, so that I can spend some effort to reduce complexity of the model to the necessary complexity. It cannot be made zero, as we know, but we want to bring this lighthouse in complex projects. So if I can bring down the complexity of the model to inherent complexity and in a consistent way, we can achieve a lot of benefit in our organization. We realize this from last 4 or 5 years. We are consistently working on this, how to bring these models in a complexity down in a consistent way, so that I can achieve the necessary lighthouse, which also is called the KISS model, as you know. So another aspect, the last challenge what we have is tools. So we have getting requirements in DOORS Next Gen. Can I have a seamless transition from requirements to functions if I am working with a Rhapsody, and then solution if I am working with a MATLAB? Can I do this? So finally, how do we overcome this challenge? We want to maximize the effectiveness of model-based systems engineering in our almost all projects, wherever we have complexity, high complexity, with a good methodology, language, tooling, and mindset. So the model is the basis for us. In a consistent way, we want to achieve this with a language which is appropriate for us, whether it is UML, Unified Modeling Language, or SysML, and then with the SPES, as I have said, the SPES 2020 as the basis, with a good methodology and with appropriate tools, we want to achieve what we want to become. As in Bosch, we talk that we intend to become an AIoT company, and we cannot achieve this without conquering the challenges that we want to do it through model-based systems engineering. So this is my presentation. So thank you very much. I'm open to questions you may have.
Thank you so much, Dr. Niranjan. We have one question for you. So what should be the approach towards traceability, especially downstream trace, when others are preparing the requirement? Should we check the whole document?
It's not possible to check the whole document. I won't recommend that you check the whole document, but traceability need to be established in an agile way. And it is possible to bring agile development into the systems engineering. So this, if we can bring, then it is possible to bring, and a consistent documentation flow from requirements engineering, if it comes until lower level software, traceability is very, very much possible. So both horizontal traceability and vertical traceability, we can achieve it. But that linking the tools starting from requirements engineering further, for example, if I am working on doors and then I am in verification and validation, how do I check this? That kind of traceability I need to start building when I am putting the requirements in doors. That time itself I should think. Normally what do we do is we always do reverse engineering, and there of course we are able to achieve SPICE on that, but reverse engineering takes a lot of effort and time.
Yes, thank you, sir. We have another question for you, sir. So which tool used for requirement management at Bosch? I'm not sure this question to be asked from you. It is company specific, but yeah.
There are many tools. One of them could be Doors Next Gen.
Okay. Thank you so much, Dr. Niranjan. We would like to thank you to give insights on MBSE and PLM.
Welcome. Good evening. Yeah.
Thank you so much, sir.
Thank you, sir. So I would like to now we'll be having sponsor lightning sessions, 10 minutes each. I would like to invite Mr. Lohan, who is Director of Projects from OBO Capella. Capella is our gold sponsor for this summit. Over to you, Mr. Lohan.
Hello, everyone. I'm glad to be here. I'm going to share my screen. Okay. Here it is. So now you should be able to see my screen.
Yeah.
Okay. Hello, everyone, and welcome to this little presentation of Arcadia and Capella. I hope you are enjoying this 2022 MBSE Summit. I'm Laurent Delegue, and for the last 15 years, I've been working for Obeo, a software company specialized in modeling tools. And today, I will give you a short introduction to the Arcadia method and the Capella MBSE workbench, and also quickly introduce the Capella community. So at the end of this presentation, you will know what's needed to get started with Capella. And in short, what is Capella? Well, it is a comprehensive MBSE workbench, and it also happens to be open source, which makes it very easy to access and use. I'd like to start by telling you the story of how Capella was born. So you may have heard about Thales, a large aerospace and defense European company. Well, back in 2005, they were trying to implement MBSE in some of their projects. They were pioneering at the time, and they had some very promising results, but the main issue they faced was that systems engineers themselves were strongly reluctant to use the SysML tools at that time. So what they did is the following. They sat together with their system engineers from different business units, and they came up with a common method for doing MBSE. And this method became what is now known as Arcadia, and I will be talking about Arcadia soon. And then they needed a tool to support this method. So they developed Capella, and at Obeo, we helped them to do so. So back to Capella. What is it meant for? Well, we cover architectural design of the system and a little bit more. We actually do also a little bit of verification, validation, a little bit of enterprise architecting, and other parts of the problem are covered. So here is basically the scope of Arcadia and Capella. So Arcadia is the method, and Capella is the tool to support that method. Okay, the main users of Arcadia and Capella are not necessarily the modeling experts, but rather they are the actual system engineers who may already be using a modeling tool or tools like DOORS, Visio Excel, and so on. This is really a core driver in the rationale behind why Capella and Arcadia were created. The goal is not to have modeling experts sitting beside domain experts, but to have system engineers themselves embracing the cultural change of MBSE. So now, what are the main objectives of the Arcadia MBSE method? Well, what are the main engineering activities that can be improved with it? First, understanding the customer need, then defining and sharing a solution for that to cover that need. So let me introduce you to the Arcadia method. But first of all, if you need to just remember one thing today about the Arcadia method, it's this sentence. It drives you to adopt certain perspectives to ensure the consistency and completeness of your architectural design. So let's see these perspectives. First of all, you have the operational analysis perspective, which is used to design what the stakeholders need to accomplish. So no notion of the system yet. Then there is the system need analysis perspective, in which you will want to cover what the system has to accomplish to support the stakeholders' needs. So we start thinking about the system here as a black box to cover the needs. Then there is the solution design, first at a high level with the conceptual architecture perspective, in which you will explore how the system will work to fulfill the expectations. And finally, the finalized architecture perspective, in which you will also, in addition, define how the system will be developed and built. Of course, with all that information is tied to requirements that remain, central in all the MBSE activity currently. And you can find here a very enlightening paper on how to augment requirements with model architecture. Okay, so now let's see a bit more about the Arcadia method. This slide displays the essentials of the Arcadia MBSE method. It fits on a ledger paper size, and you can find all the major concepts used in the method here. So on the very left of the page, you can see there are two main focuses, the need and the solutions. To capture the model needs, you will have a number of concepts available in the two first layers perspectives that I have mentioned earlier, and then the solution description will be made and design will be made in the three next perspectives that I have mentioned before. On this page, you can see a summary of all the concepts that are needed, and that's all there is to it, basically. So now let me introduce the main concepts defined in Arcadia. We use the concept of capabilities, which are partial goals for accomplishing the mission. The capabilities are described by functional chains and scenarios. And functional chains and scenarios are involving functions and functional exchanges, which carry data between functions. And we also have actors and components, of course, to describe the structure of the system that are involved in scenarios. And these components and actors have exchanges between them, and they implement functions that are defined. So that way you link the structural analysis with the functional analysis. And with that, you have a complete understanding of the main concepts of Arcadia, which are used in every perspective of the method. Of course, there are also interfaces and modes and states and a bit more, but these are really the main concepts that you need to understand. And these concepts that I just described are pretty common in systems engineering. There's nothing really new here, but their usage is precised by the method, and that's really the novelty of this Arcadia method, to really guide the system engineers on how to use these concepts in a consistent way to perform a set of activities so that they can converge in a solution that guarantees to cover all the needs that have been expressed. So let's see that by the example. First of all, let's take the simple example of a radio set and start with the operational analysis. So what the users and stakeholders need to accomplish. So that's the first engineering perspective, and it's focused on the users, what they want to accomplish, what they need. So this is something that's often missing in our systems engineering activities and tools. And we believe that we know what the customers want and need. And Arcadia says differently, we need to understand better the need of all the stakeholders that are involved to make sure we don't miss anything. So that helps questioning the way we do things, that helps questioning and challenging the user's need, and so on. Starting with this way, starting with why, is one way to identify key topics and deliver a system that better matches, in the end, the customer's needs. At this stage, we don't talk about the system, we don't model it, we just model the different stakeholders and what they need to accomplish through operational activities. We don't want to make any assumption on the boundaries of the solution. So in our example, we have a user who wants to perform activities like getting the news or listening to music and a broadcasting station. That's what we would model in the operational analysis. Tightly coupled with this operational analysis, we have the system need analysis. What is expected of the system to cover the needs that have been expressed. Here we do model the system. You see the radio set here, but it is modeled as a black box. We don't care about how it will be made. We just want to examine what it needs to do to support the needs that have been expressed. Then the next engineering perspective will be the logical architecture.
I'm sorry to interrupt you, sir. So we have only 2 minutes left for you.
Okay.
Okay.
Sorry about that. Then I will move faster on all the operational, all the analysis, and I will just want to tell you that the Arcadia method doesn't have to be applied in a top-down approach. It can be applied with any approach. It supports many processes, and the workbench is the tool that supports this method. It really is designed to help users apply the method fully, and it is designed to support the system engineers so that they can focus on doing their system engineers work, not learning on how to model, but really learning, really using the tool to just support their work, their everyday work. So there is a lot of added value in Capella, but I don't have enough time to talk about all that. So if you want to know more about Capella, just remember that it is widely adopted. We have more than 650 companies using it currently. It's pragmatic, it's ready to use out of the box and very easy to use since it is open source. It has a very active community. If you want support and if you want to discover it, here are a few links that you can go to just discover it, download it and try it by yourself. There is a YouTube channel and a LinkedIn community, a few books available, everything you need to get started. So please, I sure hope you will feel the urge to do so. And if you need additional information on how to get started or any other specific question, feel free to reach out to me. I hope that it's okay for the time frame that we had. And
sure.
That's it for today. Thank you for your attention.
Thank you so much, sir. Thank you for joining.
Bye-bye.
Bye. So do we have? Okay. So now I would like to call Renee King, our second sponsors from Certification Training International. She is Business Development Manager for PPI as well as the Managing Director for CTI, Certification Training International. So Certification Training International is our silver sponsors. So over to you, Renee.
Thank you very much, Neha. Okay, so let me see. Can you see that okay and hear me? Is everything good?
Yeah, we can hear you.
Awesome. Thank you so much for having me today during this conference. It's a pleasure to be here. Today, I just want to speak a little bit about how you might go about inquiring your systems engineering professional certification, which is an INCOSE certification. And I'm sure that you guys are hearing quite a bit about INCOSE at this conference. So I'm going to talk a little bit about INCOSE certification with INCOSE and also about how CTI supports individuals in getting SE certified. And thank you for the introduction, Nehal. I'll just continue from there. So a little bit of background about CTI. So CTI is the daughter company of Project Performance International, which has been doing training and consulting in the core fundamental nuts and bolts topic in systems engineering, things such as requirements engineering, architectural design, project and opportunity management, and topics like that. So CTI really leverages from the experience of the presenters and of the knowledge base within PPI. CTI, having been established in 2008, has trained over 3,000 people around the globe. And for pretty much since then, we've been delivering the INCOSE CEP exam preparation course, which I'll be talking about later in the presentation. And recently, we've introduced SE Cert, which is the German certification, which is quite a bit more rigorous. In fact, it's a 12-day course compared to a 5-day course for the INCOSE CEP exam prep. So we would like to think that we're on our way to becoming the leaders in SE certification in the world. A little bit of background about our team members. So here you'll see some of the people who are part of our team. And you'll also notice that we are fortunate to work with 3 lovely people in India. They are from Blue Kai, and they are our delivery partners of our INCOSE CEP exam prep course in India, which allows us to access the market a little bit more easily. So talking a little bit about INCOSE and certification. So I'm just going to assume that you guys aren't familiar with INCOSE, even though you might be. So INCOSE was established in 1990. Prior to that, it was actually NCOSE, originating in the US, N being the National Council on Systems Engineering. And it was formed in order to help to nurture and enhance the practice of systems engineering as this interdisciplinary practice that we know that it is today. It's since grown tremendously with almost 20,000 members across the 3 different sectors, that being the America sector, EMEA, and the Asia-Oceania sector, which obviously India would fall within. And there are also over 120 corporate advisory board members, and our parent company, PPI, is proud to be one of those members. They help to influence some of the policy and the strategy for INCOSE, and there are many large engineering companies that are part of that board. So when INCOSE was formed, some of the major goals that they wanted to focus on was to basically outline what the body of knowledge was on systems engineering and to help to foster collaboration internationally between different organizations, between different industries. Also to improve the quality of standards, as I'm sure we've all had experience with the fact that sometimes standards don't necessarily capture the highest quality or highest possible outline of practices. And so INCOSE is really strong on trying to improve systems engineering standards. It's also about elevating the professional status of people practicing systems engineering. It's a great way to build up your network, to liaise with people. And I've certainly learned a lot, and I've actually gained some mentors along the way. It's also allows to not only get support from governments, but also to provide support to research projects. For example, the Smart City development program that Inkosi is working on in combination with other companies to actually bring benefit to the world. So one of the ways, actually talking about the first point in terms of like building up the knowledge, as well as the fourth point really about building up your professional status with systems engineering, is to really craft your professional development with SE. So one of the ways is to work on the competency framework, which is an amazing guide out there that individuals can use to actually track their development and skill set and carve out their path compared to where they are to where they'd like to be in terms of the main pillars of systems engineering. And another major way is through certification. And certification also embodies actually adhering to Inkosi code ethics. So I'm going to be talking about the certification aspect now because this is what CTI focuses on. So the value of certification, I'm just going to be quite brief on this slide. For you as an engineer, it's really great to discriminate you in terms of the job market. If you're looking to change over jobs, if you're looking for a promotion at your current company, it really is becoming the lead distinguisher in terms of on an objective level, knowing what somebody's knowledge is on systems engineering. And in a moment, I'll talk about the 3 different levels, which I actually went through very briefly on the slide before. It also gives you a very competitive advantage in your career. If you're going to be moving countries, changing industries, at least there is that standard that you can have as a reference. And it's also just something great to work with. So maybe you'd start with the lowest level, which is ACEP, and then move to CCEP and ECEP. There's that staggered approach that you could climb over your career that will really give you something to work towards. And then on the other side, for organizations, you can imagine it really helps you when selecting the right candidates for the role. It shows that the candidate is committed to their continuous education. And we are actually starting to see it become quite common for companies to request it as part of their tender process, that they want a certain amount of people who are systems engineering certified to be part of the development projects. And this really is picking up traction, especially in the last 2 or 3 years or so. Inkosi's done a great job of strengthening or keeping, I should say, the status of the certification, because it is quite challenging. It is quite challenging to achieve your certification, and they do really well to maintain that standard. So here are the 3 levels, and basically what you need to know is if you have not been practicing systems engineering for 5 years, then you would go probably for the ACEP level. And all you need to do is pass the exam. I'll be talking in a few slides about that exam. The second level is if you have 5 years or more experience, then you want to go for CCEP, although you're welcome to enter at ACEP and then work on your experience and submit your references, because that takes some time. And then the ECEP levels if you have 25 years or just 20 years if you already CCEP. So it is quite a nice journey to pursue in one's career. So I'm just going to first talk about the experience table with regards to the CCEP level. So in addition to completing your exam, you would need to demonstrate that you've acquired this experience in these various areas. And part of CTI's training is we actually talk you through some hints and tips to help you populate that. Obviously, this is something that is done pretty much on your own, but you can get advice from people who are CCEP application reviewers, and we've got 2 on our team that are able to provide support to help you actually do this successfully. It's not Inkosi's aim to not certify people if they have the experience, but you really do need to be quite comfortable with systems engineering language and be able to identify your system of interest. So the details of it, I won't really get through, dive into, but what I will say is that over the 5 years, you need to demonstrate mastery in at least 3 areas by having conducted at least 1 year on each of these 14 functional areas. And I'll just want to talk a little bit more about those 14 functional areas.
Sorry to interrupt.
Yes.
Renee, you have 2 minutes.
Oh, sure. Okay. Thank you so much. Wow, the time really does fly. So these 14 functional areas don't actually coincide with the topic specifically in the handbook, which are the 31 processes. And now I just want to make my way quickly to talking about that. So the exam is focused entirely on the Systems Engineering Handbook, and like I mentioned, there are 31 processes that each have this IPO diagram format. And our course really does prepare you to take the exam by imbibing these 300 pages in a practical way. So let's talking a little bit about the course. So we cover these central chapters that are in the handbook that would otherwise be quite challenging to take in and to memorize. Part of our approach is to do workshops to help you come up with exam questions. And we also do a mock exam on the last day so that you can see how ready you are for the exam. And we give you a metric in terms of how much preparation you'd have to do. These are the kind of charts you can expect to see in our course, which is us reorganizing the information in a way that's easy to understand. So this basically shows you how the content of the handbook is organized and, each with the actual function that the chapter serves. This is an example of us working through a question with you to help you answer. We teach you how to read the questions, how to understand which ones are throwaways and detractors. And here is just a snapshot of the kind of exercise that we would do in class, leveraging the theoretical information in a practical exercise. In this case, applying the measurements that are discussed in chapter 4 to an actual practical problem. And this is just a template we'd use for that. So yeah, that was a very brief overview, but I hope I gave you some background about CTI INCOSE certification and what our courses are like. Please feel free to check out our website for more information.
Thank you. That was very informative. Thanks for sharing with us.
Thank you so much. I'll answer any questions in the chat. Thank you.
Yeah, we'll pose the questions from the chat to you. Thanks. So now we have Mr. Raghavendra Bhatt, Technical Manager, CADFM ANSYS. CADFM ANSYS is a silver sponsor for our summit. Over to you, sir.
Thank you. Could you give me rights to share my screen?
You must now be able to share it.
Okay, sure. So can you please confirm if you're able to see my screen and hear me well?
Yes, clear.
All right, thank you. Good evening, everyone. My name is Raghavendra Bhatt. I'm a technical manager at ANSYS for our system solutions. Thanks to the organizers for giving me this opportunity to talk to you today. I'm going to talk about integrating architecture with analytical simulation and automating the workflow management for MBSE for about next 10 minutes or so. And let's quickly look into the agenda. So I'm going to start with a quick introduction to ANSYS. Then we'll move on to discuss the need for systems engineering. You might have heard a lot about this topic since this morning, so I'm not going to really into the details. Rather, I'm planning to use this just as a starting point for my talk. Then we will talk about ANSYS Model Center MBSE capabilities to bring different tools together and enable analytical simulations to support systems engineering models, and how we can automate systems engineering workflow and then we'll conclude this session. So as many of you know very well, ANSYS is the gold standard for engineering simulation in the industry. We are nearly 5,000 people strong, and we have presence over 40 countries. Our solutions are trusted by over 40,000 customers across the globe. Our focus is to help our customers to address new engineering challenges, improve the efficiency of their designs, improve the quality, and of course, reduce the cost, all through focused simulation solutions. We have been adding new capabilities to our portfolio over the last several years by acquiring solutions that complement our ecosystem and enhance the value to our customers. One of our recent acquisitions is Phoenix Integrations, which brings the capabilities to better address the need of our customers in the systems engineering space. I would like to use this opportunity to introduce and talk to you about it today. Now, a few decades ago, an aircraft was rather a simple machine. You had compass for direction, you have altimeter for altitude, you have fuel gauge, of course, for fuel. And this one looks like it has a baseball bat for a yoke here. So most of the responsibility was on the pilot. However, jumping into the modern day aircraft, if you look at any modern day aircraft today, you will, of course, have these instruments in their latest form, of course. However, you will also find a barrage of new instruments. The analog gauges and sticks were replaced with all digital connections. Joysticks, flat screens, menus, displays, head-up displays, and many more. This aircraft is essentially a flying machine. This level of complexity is impossible to comprehend by any individual. Building such systems that are efficient and meet objectives on budget, on time, is really a challenging task. And this is where systems engineering can bring maximum benefits. However, I'm not saying that system engineering is applicable only to complex problems such as aircrafts. System engineering is valuable in realizing any system successfully. However, when the system complexity is very high, there are no better ways than system engineering approach to manage these things. And typically, when we are looking into the ways how people are currently adopting system engineering practices, we see that despite having best intentions, we see a lot of discontinuities in their workflow. So what you're seeing on the screen should be something like a continuous oval. It's like a digital engineering thread that transcends all the life cycle phases of your system engineering. And that means physics-based models and simulations, tying each phase together, being focused on the mission outcomes. So instead, what you see here is gaps, a lot of isolated models, reinvention of tools, and no common thread across programs lifecycle at all. And that results in no connectivity and no continuity of digital thread across the different stages. Not in terms of models, not in terms of physics tools, and not in terms of requirements being aligned. So not only are the models and physics-based representations are disconnected, but the physics-based representations themselves are disconnected from each other. And that means you're having new models being created at every stage, causing reinvention, duplication, lack of validation, and basically no consistency at all. The worst part, this process starts all over from the scratch as the new programs begin. The ANSYS vision for digital engineering is to have a combined, integrated, and persistent models throughout the program's lifecycle. In order to do that, we need to have good integration of models across the product lifecycle to include mission, system, physics, of course, including the cost. This consistent, continuous solution will allow you to make decisions at every stage of the lifecycle as to where to direct the resources and minimize what we typically call as scope creep that so often drives cost overruns. Repeating the earlier message, we believe in order to accelerate the program's lifecycle, it's important to create a robust digital engineering ecosystem that is comprised of third-party costs as well as the in-house tools, all synthesized and working together. Now, quickly looking into the systems models and the way how we are working with them today. So we have system models that captures the architecture, that captures the structure, that captures the behavior, and of course, including the requirements. That's one part of the story. And on the other side, we have all the analytical tools for the simulation. So you have electrical simulation, mechanical simulation, CFD, cost functions, and a lot of in-house scripts that we have written that provide us the analytical results. Now, what's missing here is the connection between these two things. How do we connect the system engineering model with the underlying analytical functionalities? And this is precisely where we are bringing in Model Center MBSE. Now, looking into the Model Center MBSE, the first thing that we want to do is to be able to provide access to the system engineers to the underlying analytical workflows. Now, on the left-hand side, as we talked about before, we have the system engineering models with all the relevant MBSE value properties. And on the right-hand side, we have analytical models with analytical properties. And we want to connect these MBSE value properties to their corresponding analytical model parameters so that you have the possibility to run through the simulation and then validate the constraints to make sure that your system engineering models are correctly going to be implemented based on the analytical results. Now, of course, all of these things are coming from the requirements. So we will be able to import the requirements. And of course, you might have multiple tools for capturing the requirement. So from there, we create the systems model, and there we create the requirements model in the system tools. And from there, we can extract the constraints and then use these constraints to connect with the analytical engineers. Now, when you are running through the simulation between this analytical model versus the system engineering model, so you will have the visibility of those properties that are actually fulfilled by your system engineering models. So you can see whether these parameters are meeting the required constraints, are they delivering the expected performance, and then what are the values that you're going to get when you're running through the simulation. So these are something that are very valuable for a system engineer, because he usually doesn't have access to the underlying analytical simulation. So either you have to create your own constraint model and you have to perform your trade-off studies for yourself, or you will have to rely on the analytical models, which basically are done by a different team altogether. By providing the abilities to connect the system engineering model to the underlying analytical models, we give you an option where you can link these two things and visualize all the simulations in one single place. You play around with the parameters. You probably change something like, let's say you're working on a drone project, and then you have a request now that the operational time of the drone has to be extended. Now, obviously, something that will immediately come to our mind is that we have to increase the battery capacity. Now, increasing the battery capacity will have a lot of unintended side effects. Something that immediately comes to our mind is that it's going to be heavier. And of course, it's going to take more space. And then the other unintended effects could be the performance of your whole system might come down. And so, is it the right approach? Should we enhance the battery capacity, or is there any other approach that we could really look into? How about increasing the efficiency of the drive motors? How about reducing the overall weight of the system? And so many other possibilities that could potentially exist. And unless we have a possibility where we can run through the simulation and see which one is the best thing. And in all of these discussions that we are having, it's important for us to keep in mind the cost factor as well. So you can see optimizing any of these parameters, how does that impact the cost, is something that's very important for us to see. And these topics are not necessarily about the analytical simulations, but it could even include your mechanical, structural simulation, CFD simulation, electrical simulations, and so on. So with the integration to the product lifecycle management, with the integrations to multidisciplinary simulation, what we essentially are bringing to the system engineering access is that you have the complete flexibility of performing multidisciplinary analysis and optimization capability, and the access to host of such algorithms and post-processing. Of course, these are not coming directly through the MBSE solution. These are the capabilities which you already have in the organization. What we are bringing in here is a mechanism where the system engineers can easily access these underlying algorithms and see the simulation results over here. So that's basically our vision, wherein you can completely start right from the requirements, and then we create the system descriptive models. The model center comes in here to connect these with the analytical models, and then you can perform your typical trade-off studies. And then the results of the trade-off studies are pushed back, and the model is going to be updated, and we check whether the requirements are still met and the designs that we have created are still compliant. And then this, of course, is a cycle that continues until we arrive at the best possible solution. So that is primarily what I wanted to talk to you about today. And once again, thank you very much for this opportunity. And the last thing before I exit, I just want to flash this opportunity that we have. We are hiring people for system engineering roles, and we need someone that could help us in effectively communicating the value of our solution to our customers. So this is an opening in our pre-sales department. We are hiring for senior application engineer. So you could go to careers.ansys.com and you could just search for MBSE, and you will come across with this particular job. So you see here the requirement ID, title, and so on. So I request you to, if you are interested, if you think this is an interesting topic, please go over here, apply for this. And just in case, if you want to directly connect with me, you have my email ID as well as the phone number as well. So please feel free to connect with us. We are looking for right set of people to help us on this topic. Thank you very much.
Thank you, sir. Thank you, sir, for sharing this opportunity, and also providing us insight about that tool. And thanks for completing on time. Thank you.
So we are following system engineering process. It
Yeah.
should happen on time.
Thanks for sponsoring us. Thanks.
So now we have panel discussion. I would like to invite Mr. Etienne, founder and vice president of OBO, Mr. Vijay Dodavaram, director of digital tech, Collins Aerospace, Rajesh Singh, who will be the moderator, lead systems engineer, MBSc at Boeing India Engineering, Mr. Jawahar Bhalla, principal, JB Engineering Systems, and IPhD candidate and University of Adelaide and Scholl Group. So I would like to invite all of my panelists here. Over to you, Rajesh.
Thank you, Neha. And yeah, once again, I welcome the panel members and good evening, good morning to all our listeners, right? So, okay, so we are here to discuss about the topic around future of digital engineering, right? So when I say this word, I try to think back, like what does it mean to me, right? So it's a two word, right? It's the first one, the word said digital, right? So when the digital comes to our mind, we tend to think about, IT, computers, right? And maybe programming, right? Applications, and the other word, engineering, that kind of leads to us like, well, some physical form of maybe models or could be some formulae, right? So this combining this word digital and engineering together, right? So when this comes together, it has a significant relevant, right? Both from the product-centric perspective and also from the services point of view, right? And digital engineering landscape kind of applies to every possible industry, right? So this is kind of an informal introduction to the topic. However, yes, we'll hear more in detail, right, from our panel members, their experiences and what's the future of digital engineering lies ahead for us, right? So I'll throw this question to them one by one. I'll invite them one by one. So first question would be like, what's the formal definition of it, right? And we'll try to cover some additional generic questions, right, during the sessions. And yes, I encourage our listeners, audience, or participants to post their questions in the chat, which we'll try to take up at the end, right? Or maybe in between as well. So yes, let's go first with JB. Are you okay to go first?
Yeah, sure. So do you want me to do the presentation first, Rajesh? Is that okay?
Yeah, all yours. Yeah, the way you want. Yeah.
Okay, I'm sharing the screen then. Here we go. So if this works. And Rajesh, if I start to go towards the 10-minute mark, just tell me, all right, I'll stop. Yeah.
Thank you.
Okay, so I just wanted to share some insights or thoughts on the future of digital engineering, coming at it from a modeling and simulation perspective. You probably, not many people have heard this word, but I find this to be perhaps one of the most powerful words currently in vogue for what we're trying to do. So this word came from David Snowden. He's the one that sort of coined the term exaptive. David Snowden is the guy that came up with the Cynefin framework that I have found to be a really relevant framework to understand the world around us and deal with it. When typically people deal with it in a linear sense, you know, sometimes it's not linear. It gets complicated, gets complex and chaotic, and there's a massive framework over there. But the point really I want to focus on is this word exaptive that he coined. And he said that it's really about repurposing. It's about taking an idea or a concept, a tool, a methodology or framework from one context and bringing it across and applying it in another. And so I want to sort of dwell on that a bit and very quickly talk on these 5 topics, very fast. What the challenge is, the situational awareness, sensor fusion, modeling and simulation, and integration. So I want to start off with the challenge. I mean, the world we live in today machine learning, artificial intelligence, technology just blowing things away. It's changing the way we live and changing how we have to deal with the world. We've seen it in the transport industry, cars, Tesla and so on, massive change happening, and seems to be that's where it's focused. But it's happening everywhere. It's happening in autonomous systems in the marine context, in the air context. And in fact, we're starting to see that the advent of these advanced autonomous vehicles is truly going to be one of the biggest challenges and disruptive technologies that is going to change the way that we live. And we've got to learn to adapt and to be able to work with these systems to make them safe and secure. In Australia, for example, the defense side of things, the Navy has recognized the importance of autonomous systems, and they have a strategy that focuses, front and center on autonomy and how it be dealt with. The robotics roadmap that was just released in Australia talks about developing a governance systems for robotics, so that we can trust systems in this context. The problem with all of this stuff is the technology is moving so fast that the means to ensure that technology is not happening as fast as it should be. In fact, data shows that 47% of projects fail in the machine learning AI construct because they actually don't have there's a lack of tools, there's the inability to connect things together to get to the level that we can call them production grade. And in essence, while we're creating these building blocks all over the place, the challenges we find is about connecting these building blocks together. And so there's clearly a need of this holistic view of software intensive systems that we've touched on across the board, from Dr. Koda to start with and through the other presentations. And so there's a need to look at how we engineer safe and secure systems in that regard. And what I've sort of, and one of the challenges that I'm looking at in my research is coming up with the systems engineering framework for this. But what's really coming out to me as I'm doing more and more and trying to understand this is that really it comes about the inability of our current constructs for models to connect. For us to be able to understand and for models to be able to understand in the bigger picture what things are. And there's a term that is used in defense for that, and it's called situational awareness. And the challenge I think we face is how do we get common situational awareness across capabilities that will allow us then to make them safe and secure. So I just want to quickly expand on situational awareness from a defense context. So when we look at modern day defense capabilities, they're distributed. We have land forces, sea forces, air forces, space even, and all of them have to connect, and to deliver a capability or a particular mission, they have to have common situational awareness. And Micah Ensley talks about a model for common situational awareness. He calls it a three-phase process. We perceive the environment through our senses or our sensors, depending on the platforms we might have or autonomous systems. We then use the mental models we have to comprehend what the situation is, and then we project the future by simulating what could happen. We make a decision and we perform an action, and that changes the environment, and that loop continues. And how well we do this depends on our situational awareness and that of everything around us. And in the defense construct, there is a very regimental way of training people up. So we start off with individual procedures training, and there's a very good framework to do that. For example, in the Air Force side and the air side of things, high fidelity flight and mission simulators get you to the point of zero flight time trains. You can go and fly straight up. However, as we get above and we start to connect things together, that's where it starts to fall apart. Now, this happened about 10 years back or 15 years back in the air domain in particular, where the challenge has now been overcome. But even so, the preparedness at the mission rehearsal at the distributed training level is pretty limited because of the challenges that they face. And that resulted in a paradigm shift about 10 years ago about how training systems were developed so they could interoperate. And interestingly, I saw that come back again in the technology and the architecture of the F-35, the fifth generation fighter. Now, you probably all heard about the F-35, but the fundamental difference between the F-35 and the fourth generation of the 4.5 were really the stealth and the sensor fusion capabilities. It took it to the next generation up. And what it did was, again, a mirroring of exactly the same concepts in the modeling and simulation space. So, for example, if we have these three aircraft, three different generations, and we're trying to look at their sensor systems, what we find is that the previous generations were looking at a concept of more integrating sensor information, while F-35 comes in and brings in a sensor fusion context. So, for example, if you have sensors A, B, and C on these aircraft, what's happening in the previous generation is these sensors are acting independently. That information is being transferred over a tactical data link and then being integrated on each platform, and they're trying to develop situational awareness as a common performance picture. In the F-35, the sensors are fusing data that's coming between them to develop that common picture. And this concept is repeated in a framework that has evolved for modeling and simulation in defense, where you look at the participants and the environment and whether they're real or not. And we come up with these 4 categories of live, real people, real environments, virtual, real person, simulated environment, constructive, completely digital, and then we simulate the human in the environment. And if you look at the virtual construct, on the right-hand side here is a classic example of how the virtual architecture might sit. So we have a simulation of a platform with its subsystems, sensors, weapons, avionics, airframe, the environment, the synthetic natural environment, the tactical environment, some sort of instructional environment, and enabling systems. And then we take these subsystems and we integrate them together to deliver the capability that we're trying to deliver. Now, what happens when you try and connect simulations together? What we're actually trying to do in that context is actually connect at the subsystem level. We've got to get all of these common subsystems connecting together, and that's where it falls apart. And what we find is when we take it into the full live virtual constructive construct, we've got to have it make that challenge becomes even more. And the fundamental lesson learned is that in order to do this, we've got to have 2 different paradigms. So we have to have vertical integration and we have to have horizontal fusion. So our models at the subsystem levels must allow for the concept of fusion. In other words, we augment each other and not just about translation of information, and we need to integrate vertically. And with that insight, I'll sort of finish off over there. And again, come back to the point of, when we talk about systems engineering, it's really about engineering systems, and systems thinking, modeling, and simulation are absolutely fundamental. I think I might have gone over time. Sorry, Rajesh, I'll stop sharing now and I'll come back to you. Thank you.
Oh, thanks, JB. That was in-depth study. Thanks for sharing. Thank you very much. Right, so maybe Mr. Georgette, would you like to share your experience, details about the topic?
Yeah, with pleasure. So let me share my screen. Hello, everybody. So, can you see my screen?
Yeah, we can. Yeah.
Perfect. So, hello, I'm Vice President of OBEO, and I try to summarize in only one slide my vision of the future of digital industry. So I would say that there is 3 steps, one which is in the short term, another one which is more long terms, and it's also 3 steps in terms of maturity of adoptions about the digital engineering and mainly the system engineering side. So let's start by the first one. So as I think one of the big change which is already today partially covered is to ease the onboarding. One of the issue that we see in lots of engineering teams is to see teams which is organized with some people which are expert in electronics, in defense, in automotive, and some other which are the, let's say, the expert in system engineering, which are here to collect and capture the analysis made by somebody else. I think one of the big change here is to spread the word, to be able to put in the hand of every engineer, whatever is his specialty, or the power of system engineering methods and tools. To do this, to democratize this aspect, one first key point is to enable the methodological guidance for the daily usage. If you start with a blank page with several hundred of concepts, you go in the wall. So you need something very easy. So today, there is already one famous methodology called Arcadia, which comes from the handbook of INCOSE, and which help to provide such guidance and to again avoid the blank page effect. You need also some future to not have just a paperwork methodology, but have the methodology inside the tools. So my personal vision is to rely on an existing open tools, which is completely fit with Arcadia, which provide this guidance for the daily usage and which provide productivity tools. when you need to go from operational to system to logical design, you don't need to reinvent the wheel, and you need to have some tooling to accelerate your different transitions. And that's the kind of stuff which is very useful for large adoptions. And then something important, if you see the general market, is that people want to ease the access to the information, to ease the deployment of all such solutions which can combine server, client-side tools. And so I trust in a ready-to-use environment. So we create, for example, Cloud for Capella, which is a kind of cloud-based, ready-to-use environment. You just needing one click to access your data with everything ready to use. I think it's something, lots of tools in the digital engineering industry. It's still with desktop-based tools. And I think in the next decade, we will go more and more on the web. We will go more and more on easy to deploy and easy to use access to democratize this. The second step is to scale. At this level, you want not only to onboard your system engineering team, but also to extend this to larger project and larger teams. So first, you need, my vision is to ease the daily usage for the system engineering team itself. Everybody on this call already use Google Docs or the new Office Online experience, where you can modify in live with several people in the same time the data. And I trust that this user experience is really a game changer to simplify the access and the live collaboration between people. Secondly, one key aspect is to scale on a very large systems. If you try to put several hundreds of people on the design on the same aircraft, let's say, it will fail because you will not be able to stabilize one official versions. You will have modifications several times per day on every part, and you will not able to have a baseline. So nice solutions is to use system to subsystems transitions by having models which describes the integration, and then you have some systems which are black box, and you derive them in other autonomous models dedicated to other teams or suppliers. So in this way, you can manage the suppliers, the work of suppliers, and you can also manage the integration by keeping link between the parent model to the children models. Another part for enabling this to scale at a large scale is to couple requirement and ILM work items with your digital models of your system architecture. And I think it's really something important which should be made in parallel of your design. And then by doing this, you enable a traceability, of course, but you also propose to people outside of your teams the ability to better understand the requirement. So you can, just by following the requirement, see some consult some diagrams, consult some detailed data of your system engineering, and so you again democratize the usage of system design to teams which basically are not system engineers, but they consume these models to better understand in a common language their integration point and what the functions they have to implement. Last point is a digital thread. So this part is clearly about digital continuity and avoid to have some breaking point where you come back on Word, Excel in your flow of engineering, and you use model everywhere. So to do this, there is let's say kind of backbone in lots of large industry which are based on PLM, and one key change is to enable the coupling between system engineering tool to PLM and their BOM, or bill of materials, because the system engineering models is really let's say, implementation neutral. It should be exactly the same models for electrical guys, for mechanicals, for 3D, for simulation, and for everybody. So it's really need to be at the core of such a PLM and A to Z life cycle of a product. Another challenge is to standardize the data exposure not through a data exchange, but mainly through modern web API. And for this, I trust in SysML as a way to standardize the output of lots of engineering tools. And I think it's a nice way to enable a large-scale interoperability. Also think that nice change for the future is to really enable the transition to downstream tools. So you manage your architectures, you click on a button, and it's automatically generate or initialize a kind of stub of your electrical design, of your mechanical and so on. And if you modify inside your electrical, you have the closed loop, say that it will help you to come back on the architecture's design in your system engineering tools, and then master the impact on all the other teams. And in this way, I think it could help to have a system more agile. You can better master impact, not at the month level, but at the week or even the day level to better enable digital thread at the digital twin, sorry, but at the architectural level of your enterprise.
Thank you, Mr. Jolit. So yeah, that was good information on easy and then scaling it up and then from the long-term perspective, right? Thank you very much. Right, so you can stop the sharing, Mr. Jolit. Thank you. Right.
I did.
Right, so I call upon our last panelist, Mr. Vijay. Would like to go next and give your views, your experiences on this. Thank you.
Am I audible?
Yep.
All right, great. And I hope you can see my screen.
Yes, thank you.
Okay. So what I would like to do, and when I saw this topic, I approached it from a product management perspective. And Rajesh, I like the way you framed it, digital versus engineering. So when you take a software product management cycle and a engineering product management cycle side by side, I mean, there are many hundreds of things you can call out as distinctions, but two things I would like to call out. One is the cycle time, which is how long it takes to rev through, one version to another. And when you look at software products, you see a new release or a minor release every couple of weeks, a major release maybe every 6 months or so. Whereas when you're manufacturing things, that release cycle is typically years. And there's a reason for it, because it has to go through design, manufacturing, validation, etc. The flip side of that is reliability. Software products typically, we are tolerant of a lot more unreliability, bugs and such. In engineering, any engineering situation, we are far less tolerant of reliability issues. So, and to me, digital engineering is an attempt to pick the best of both. So how do you rev faster through product generations and still deliver high reliability? I think that's the real promise to me of digital engineering. So we've heard everyone talk about it, right? I mean, it's the buzzword, this whole digital engineering, digital thread, all of those things, they're all over the place. So here are some stats I pulled out. So McKinsey feels in the aerospace and defense sector alone, there's annual savings of $20 billion expected through digital engineering. And here are some stats around where people use it, again, in the aerospace and defense sector. This is again from McKinsey. So you see it's in supply chain, it's in R&D, it's in manufacturing, it's in support, and it's in aftermarket, which is, I think, a huge area for this industry. However, that's the promise. But what the reality is that the recent study by BCG says only 30% of these are successful today. And which means 3 out of 7, 3 out of 10 is where you see results that you thought you would see, and the rest and the other 7 you don't. And I think that's where I feel we are at an inflection point in the space. A lot of enablers are changing, and typically in the software space, you talk about the flywheel effect. Some things kind of feed into the process, and as you grow, as the whole thing grows, the flywheel runs faster and faster, and it kind of builds a lot of momentum. So that's what I think is going on here. Just as a data point, I pulled the sales of AR headsets worldwide, AR, VR headsets really worldwide, and this is a combination of actual data, past data, and future projections. Now think about it, when Facebook talks about Meta, when we talk about metaverse, and that's in the consumer space. Think of the potential that UX tech like AR headsets can do in the digital engineering space in the enterprise, whether it's design, manufacturing, support, aftermarket, things like that. So I think that's just one key enabler, I think, that we're approaching an inflection point. Similarly, I heard JB talk about ML and so on. So across any large engineering product generates a ton of data every moment it's working, whether it's an airplane, an engine, a large piece of power generation equipment. It generates a ton of data. And that is both a boon and a curse, because a lot of data means you can do a lot of analysis, but a lot of data also means that you have no idea which data to pay attention to. And that's been a problem. That usually the reaction or the way we've handled it is we just ignore a lot of the data. And that's, we've heard this, right? Data is the new oil. So processing on the edge really helps us train algorithms to pick out data, patterns, trends that we need to incorporate into our systems, so that we can kind of eventually get to a closed loop kind of model, right? So you can, the real life product feeds the system model, and then changes in the model feed the real life product. So I think that's really another key enabler. The third one is the ability to rapidly prototype at scale. I think Etienne talked about prototyping and scaling, for instance. It used to be that only companies that had huge investments in digital could do anything around digital thread, because the sheer volumes of data, the simulation horsepower that's needed, the technical skills needed, etc. I think it's increasingly becoming democratized, in my view. And the fourth one I think is really important, because a lot of digital thread talks about what we will do in factories of the future or design processes of the future. But the truth is, a huge amount of investment, billions and billions of investment have gone into technology and factories and design processes and tools that are legacy today and do not have a way of becoming digital easily, or should I say did not. I think a lot of that, we're having better solutions around how do we pull the legacy tech into the present. And the last one to me is the skill pool. It used to be really hard to find people with expertise in these areas. If you look at Bangalore, if you look at any of the large technology centers anywhere across the world, that's becoming a lot less of a problem. So key enablers. So what does all this mean when you put this together? So I want to go back to the software product versus engineering product kind of a delta, right? When you have long cycle times, you tend to take smaller risks with each incremental generation, because you take a large risk, you take 6 months building it out, manufacturing it, and then it turns out it doesn't work or it is a problem. So you go back to the drawing board. So the downside risk was huge, and the way typical product managers addressed that was taking much smaller risks, where they felt the probability of success was higher. That constraint hopefully will go away in the future. We can take larger risks because you can do this through digital engineering. You don't have to go through the entire manufacturing cycle to find out what problems you're likely to hit. And that just makes the rate of innovation so much faster. It also means safety dramatically improves, because you can find more issues earlier in the process, in software, in the model, as opposed to trying it out in real life. And of course, it just makes it a lot more democratic. So you can actually tap into, once the ecosystem, once the flywheel gets going, it just becomes easier to build your models that incorporate larger and larger subsystems into your design. so that you can model behavior across a larger scope. And this is, of course, much further out in the future. So that's kind of how I see the future of digital engineering. And like I said, I think of it from a product management perspective. Thank you, and happy to take questions.
Thank you, Vijay. That was well put, backed up with the data. Thank you. Right. So yeah, we heard details about the topic from our panel. Right. So I have a few generic questions. Right. Well, I collected in support of the topics, right? So the next one that I have is like, I think we got a sense on a generic point of view, like how important is digital engineering to our business, right? So it's open, anyone can take that. So if you guys want to kind of talk about a specific use case where digital engineering is important to your business, yep. Any specific use case? Yep. Either, I mean, you can raise hands or like, well, it's open.
Okay, so maybe I can start. So think of a typical manufacturing, design to manufacturing to support process, right? There is a lot of data that gets created during the design phase, testing, verification, etc. And then the product moves into manufacturing, and there's a lot of validation data that gets created as well. I think there's huge opportunity, and I've seen this being in small use cases. Do, for instance, things like what is the thermal performance of a certain device under real life conditions, right? So, for instance, if you want to see how a certain device performs at -40 degrees or +150 degrees, it becomes so much easier when you start building a parametric model that lets you do that, as opposed to the traditional approach, which is actually put it in a thermal environment physically. Build it, put it in a thermal environment, test it, and see what happens, and then try to figure out, okay, what exactly failed, because you don't have it. The physical part is much harder to instrument to capture details of failure as opposed to a digital model. So to me, that's an example of where digital engineering can really make a huge difference.
That's very, I mean, the first use case or yeah, very important use case in support of digital engineering, right? Yep. Okay, JB,
maybe I'll just add a very quick point to that. And if you look at the the whole of life or a life cycle capability, cradle to grave, we have MBSE being applied at the front end pretty much, and for the conceptual design, basically needs to functional architecture, logical architecture, and then to some extent we map it into the physical architecture through an allocated baseline. But then there's a disconnect typically, and then we build a system, and then we feel the system, and then there's almost a backward flow happening where we're trying to recreate a digital model of the physical system. So we don't have this holistic end-to-end connectivity, traceability, so that we have one model that goes all the way through and then becomes a digital twin at the end. And I think the value proposition that would provide would be phenomenal, right? I mean, truly phenomenal in terms of all the points that Vijay was making about, the learning from all of these things and building up your data over time and having all this information that you go back to so that you could run things, check data, and do all of that stuff. And so that's the ideal vision. And I think there's the challenges that we're seeing over there are very similar, and that's why I use the flight and the defense and flight example also, because this is partially sponsored by the aerospace side of things, is that those challenges, especially in the high fidelity modeling and simulation space, were showstoppers, right? You couldn't conduct a mission rehearsal with people all joined together in a common environment because everyone built things in a proprietary fashion. All models were done differently, and that resulted in this is going back about 15 years, and I was really lucky to be part of this and happened to see this happen, was it broke the architecture. It said, if you build architectures like you're currently doing, there's no way we can ever do that. And so we have to change how we build simulation architectures. And one of the things it did was the recognition that the simulation of the environment, the world that you're operating in, you can't have your own world. We have to have a common world that everyone is in. And that resulted in a complete paradigm shift in architecture. There were three things that came out of that. And I think in the digital transformation, we probably will go down a similar path. The first thing was that we had to come up with a common format or way that we would store models for the environment and models of entities. The second thing was that people wanted to protect their IP. And so, well, we can store it in a common format, but I'm not going to give you my model. And so there was a need to be able to exchange state information. So if you didn't want to share your IP, at least you can share your state information. Where am I, what condition am I in, how fast am I going, and what am I doing? And the third part was that the architectures had to be runtime bind. You can't have compile time bind architectures for these things. They have to be runtime bind, because that's the only way you can just plug and play and come into this thing and do it. And I'm not seeing that happen yet in the MBSE, in the systems engineering space. And I think it's a natural progression, but some of that is to do with proprietary and people are really reluctant to open up the formats and to do that stuff. But I think there's a paradigm and a lesson to be learned, in what happened in the modeling and simulation space, primarily in defense. And this was driven by the US and the special operations guys that wanted to do this mission rehearsal. And so I just want to make that comment, and probably spoken too much. So back to you, Rajesh. Thanks. Yeah.
That was a great point to add to that. Yeah, thank you. So maybe I'll come to Etienne in the next question, right? Very interesting one related to the environment we are in. So the question, it's very interesting, like digital engineering growth amid this pandemic. Has anything changed, right? With this pandemic around? Digital engineering growth amid this pandemic. Yep. You want to tag that, Mr. Jose?
Good questions. I think just in terms of the value of a digital model here is higher when you work remotely and you are not on site. So you cannot just physically be able to work on particular paperwork flow. You really need to have a smoother way to exchange data and to work fluently with your colleagues. So for this, I think it's really help to see the value of working directly on digital models. And at one point you mentioned the difference between digital and the physical model. Clearly, because of the pandemic, if you are not on site, you don't have access to your physical systems for simulation and for some design stuff. So you need to have this digital mockup and also the functional mockup. So I think it's helped in a way. I also think that it's helped to understand the value of using digital model on existing systems. If you want to just not reinvent a new system from scratch, but you need to do evolution on an existing one, which is on one of the survey we made on the open source community around Capella, it was around 75% of the project, which were about existing systems. You just need to make a little evolution or need to do a kind of reverse engineering of the existing. And in this way, working with digital aspect and simulation analysis, system analysis, sorry, is really useful because you discover the physical, you ask people to explain you the functions applied to this physical, and you are not loose in too many papers, too many documents which describe the legacy, but you succeed to keep a big picture and overview things of the graphical aspect of any system models, and you succeed to master the complexity of something. And so you better you are more efficient. You are more efficient when you need to do just a little improvement.
Thank you. Thank you. Yeah, that's a good point. And I think with this pandemic around, there's a lot more stress, demand, or the need for more ways to do digital engineering, right? I mean, okay. Yep. Thank you. So I think let's go to the next question. We cannot miss this. So the challenge associated with adoption of digital engineering, right? I mean, we cannot miss this question. So yeah, any views? Vijay, JB, you want to pick this, either of you?
Sure. So I think I'll give it a shot, and JB, maybe you can also check. This is how I view this, right? So I think JB talked about interoperability as one challenge. So there is a balance you have to draw between protecting your IP versus exposing, that's not bad, providing an interface to the digital twin of whatever subsystem you've designed. Right? You want to hold the IP close to yourself, but you want to be able to provide the performance characteristics, modeling characteristics of your subsystem, so it can integrate into a larger model. So I think that's always going to be a challenge. Where do you draw the line? Because you could argue that if it's a detailed enough digital twin, maybe it's reverse engineerable. So that becomes an IP problem. Another challenge, of course, extending this is the whole cybersecurity thing, because it's now you can go, there's layers to this, there's levels to how digital you want to be, your engineering want to be, right? If you're operating at simulation level, the risks are one, as of a certain magnitude. But if you set up a closed loop optimization model where your digital model can actually impact your physical model, your physical reality, the chance of someone unauthorized getting into your digital model and therefore affecting your physical model, the risks associated with that are huge. The third thing I think is, those are, I guess, the glamorous sounding risks. They're very Mission Impossible type of risks. The third thing, of course, is you have all these factories, design processes that have been operating for the last 30 years. How do you make them digital ready? I think that's a big challenge.
Thank you, Vijay. JB, you want to add that?
Yeah, I could, but that was an excellent summary by Vijay, really. So I probably want to add from two perspectives to that. So one is just leveraging off the last point that Vijay made, is when we have to recognize that we are very seldom going to have the opportunity to do greenfield development in anything today, right? There's stuff already there, and we're going to have to build capabilities that plug into other things. And as we go down this digital path and we go into machine learning and things like that, what we're finding is that the points that Dr. Kota Harinaran made at the very start, right? That we have to think about the implications and the interfaces that these things interact with. And most importantly, the human interface with that. I mean, classic example, right, is the 737 MAX, is the introduction of the, the MCAS system in there. That in a sense was a bit of artificial intelligence, right? It changed the pitch of the aircraft depending on what the conditions were, and it wasn't rolled out properly. The human element wasn't factored into the picture, and long story short, and I mean the details are there, we ended up with disasters, right, when that happened. So we really have to be very sensitive about introducing new technologies and capabilities, especially in this digital construct, into existing systems. And the challenge is that that's what it's going to be all the time. And so that leads on to the second point that I wanted to make, was we also, these systems and this digital transformation is happening so fast that the safety envelopes that we could provide in the past aren't keeping up with that. So regulation and safety reference architectures are actually catching up to what these things are. And that's part of one of the areas that I'm looking at, is how do we build the integrity and safety into these systems, and then how do we assure them going forward through their life as they learn stuff. And right now, the model is pretty much leveraging off the typical DevOps type cycle, but it's not a learn as you go. It's a you learn, you feel the model, and then you come back and it doesn't learn on the fly, right? Because we can't control how it learns on the fly. It has to be controlled. And so that to me is a massive challenge, the assurance aspect. How do we make systems safe and trusted? And what is different about systems engineering or engineering systems that allows us to do that? And again, I think we have lots of lessons learned from modeling and simulation that will show us that and say, this is how we trust models. And I think we have to remember that and bring that back in, because we're moving completely into digital model age, right? And our ability to trust those models is going to be fundamental. So yeah, thanks, Rajesh.
Very good points. Thank you, JB. So yeah, digital engineering, it's need of the hour. Well, there are so many benefits, but yep, very good use cases being pointed out. So we need to consider the risk and the opportunity, which goes hand in hand. Thank you very much. Yep. Right. So let's take another question from our generic pool. So yes, we are in an MBSE summit, right? So MBSE role. Where do we see MBSE role in the future of digital engineering? Right. So it's again open for the panel.
I think, I hope so, that it could be used as a kind of orchestrator across teams. Today, I think one of the change is the communication and the ability to work in a short increment between teams, which are mainly through silos. So you have some, as I say, my first introduction, you have some electrical guys, you have mechanical guys, and they are synchronized just across some meetings. Like they can do one time per weeks, or just across some specifications, steps, and it's not enough. If you really think that the future of the engineering, modern engineering flow, is to enable an agility which cross the skills, cross the team for daily evolutions, I think MBSE will be really, really key. Because if you want to master the impact on a cable, just a physical cable somewhere, and you need to, and you do connections of impact analysis between this cable to the 3D system, to the simulation, to the software and so on, it is a nightmare. And lots of the customer and user I speak with doesn't really see the issue currently. And MBSE is key to be a central piece where you increase your abstractions. You are not deep in the details. You keep the big picture, and then you can easily speak with the other team without be lose in too much implementation details. And I really think that communication across teams is key.
Perfect. Totally agree with that. So communication, reusability, and as you mentioned, yep, single source of truth, modeling environment, right? Yep.
And just to comment on this, and one concept I see from my experience in several years to explain this to newbies is really the functions principle, the functions. Because when you show them static component-based design, state machines, sequence diagram, and so on, you say, okay, I have the same in my electronic system, I have the same in my software, and so on. When you speak about functions and allocation of function on physical component or logical component, sorry, it's completely changed again. The function is really key because most of the time in implementation tool and implementation workflow, this function aspect is something which is a little lost in lots of specification and not clearly identified.
Thank you. Yep, good points. Good point. Right. So, gentlemen, we are on top of the hour. However, I think we'll take a couple of minutes to answer one of the questions from our audience. So, I think I'll summarize this. So, what our take from the digital engineering perspective on the legacy products, right? So, I mean, in short, if anybody wants to summarize this or give it a shot on the legacy product, digital engineering.
So the big challenge to me on legacy product, when you want to move legacy products into digital model, is digitalizing it, I guess is the word. how do you, let's say you have a machine that does some things, that's part of your production line. And how do you model that, essentially virtualize that machine into it in a way that you can plug it into your digital, overall digital twin rather, so that you can kind of, what the machine really does in real life, you can capture in a model, and therefore you can use the model instead of actually using the machine. So the digitalizing process is probably the most labor-intensive step. Now, the good thing is, typically any component of a value chain that's been around for a while has reams and reams of test data. So the data exists. What does this particular thing do under these conditions? Someone's captured it somewhere. It's probably in an Excel spreadsheet or book or paper or something of that nature. So one thing you could do is put the machine through a standard process to capture its performance characteristics, and therefore digitalize it. But hopefully the better way is look at what test data exists over decades of use, and how do you use that to create the model. And the second thing, of course, is coming up with standard protocol. So Lego is my favorite example. Right? There are 1,000 different varieties of Lego blocks, but they have an interface that stands. So any Lego block will work with any other Lego block. So coming up with a model that you can capture the individual subsystems into a standard format that's understandable across the entire model. I think that's the other thing. The third thing, there are plenty of tools now available like GraphDBs and so on that make it easier. So I think, and conversational AI makes it easier. So some of those things help solve the problem in a better way than we used to be able to.
Perfect, Vijay. Thank you. I think that's a step-by-step approach, right? For the legacy, digitize and then digitalize, right? Thank you very much. Right, gentlemen. So thank you. I mean, it was great talking, getting so much detail, data, facts, and so much of information to digest. Thank you for your time. Have a great day. Thank you. Over to you, Kalpesh.
Bye-bye.
Thank you, Rajesh. Such a wonderful talk. Yeah, I'm really mesmerized. Thank you, panel of speakers, for having such a wonderful discussion around the future of digital engineering topic. It was really a valuable inputs from all of you. Thanks. So coming to our next talk, I would like to invite Dr. Ranjan Vepa. He is a PhD from Applied Mechanics from Stanford University, PhD reader in Aerospace Engineering in School of Engineering and Material Science from Queen's Mary, University of London. Over to you, Dr. Vepa.
Yes, thank you. I'll start sharing my video in a minute, just 1 minute.
Able to see?
Start sharing my screen. Hang on, let me just start sharing. I think you have to give up the screen or something before I can show my screen.
Yeah.
Right, okay. Okay, can you see my screen now? You should be able to, and I'll put it in, oh.
Yes, I'll be able to see it.
Yeah, I'll put it in slideshow and full screen. Right, what I'm going to be talking about, basically I'm with the School of Engineering at Queen Mary, University of London. I'm right now, of course, teaching there. And what I'm going to be talking about is model-based systems engineering from an aerospace perspective. My main focus is actually current aircraft and future aircraft. Mainly, of course, future aircraft, when I say, is all electric. That's where we're headed. Although you may not see it in the current products, because I'm going to explain why very soon. But the overview of my talk, basically, I will start with an example. And to me, UAV is itself like an example, a model. UAV doesn't actually mean UAV, and you will see what I mean very soon. But that's a good example to start with, and we'll look at all the systems engineering process and why model-based systems engineering is absolutely important. And of course, some of the things we do, some of the simulation, we do a lot of simulation A lot of it is based on things like Simulink, but there are other simulation tools as well. So just to give you a picture of a UAV to start with, I mean, that's really not the whole story. I mean, to some extent, that's the starting point. I won't go through all the subsystems and so on, just to give you a fleeting view. Probably I will run through some of these slides a bit faster at some points because I have quite a few. They're just there to remind people of what we're going to talk about. The first thing to start when you're thinking in terms of a design of an aircraft and so on is look at the entire, start right from the beginning. You'll be surprised how much you will learn. Start with Leonardo da Vinci, who was actually a fantastic guy, and he thought of everything quite long time ago, and you'll be surprised to know the Wright brothers actually implemented his ideas. I won't go into that story now, but that is really amazing. And of course, we're going down the line, Boeing, Predator. Most of you probably know the Predator story, how it came about. They challenged the regular aircraft industry and got it right. And now, of course, now we are with electric aircraft, and pretty soon we'll be looking at the future, 2050 and so on. We have to plan for the future. Look at all the developments if you're planning a new project, and of course, move forward. Of course, aeronautics is a very old field, and one has to remember that. It started a long time before 1903 and moved on several phases. I don't know how many of you recognize that first aircraft, very famous aircraft, also a Boeing, and basically some really tremendous aircraft have been built. I'm just jumping from slide to slide over 50-year periods. So basically you go over to the time when all the UAVs, Predator and so on were sort of developed. Of course, my focus is mainly civil aircraft. And of course, this is the latest proposal from, almost the latest proposal from Boeing, autonomous air taxi. But there are newer proposals which are still, of course, they're in the design phase on the drawing board, some of which are covered by non-disclosure agreements and so on. But we are getting to, the point where we'll be looking at autonomous electric aircraft for the future. Why autonomous? If you look at aircraft systems design, I mean, it may not be entirely obvious at the beginning, but it turns out all future aircraft now are probably expected to have an autonomous mode. Just like the current aircraft, you can just go to the flight controller and switch on a button and say, or put it on autopilot. You'll be able to do that and put it on autonomous mode very soon. It won't be very long before that is actually completely feasible. And I know several companies are working on that, and some have actually perfected the system as well. It just has to sort of come out into the market. So very soon those things are going to happen. And the aircraft industry always has to look 25, 30 years ahead. You may not know the Concorde story, but the Concorde started in 1949. And it took about 24 years to develop. And then, of course, it was around for 27 years. And boom, it went off in 2000. And that was the end of it. So that's the kind of sort of timescales we're talking about. And that's what we have to look. And the primary feature of a UAV, and that's one of the reasons why we sort of consider it, is the autonomy. Autonomy is the ability to work by itself. The goal of an autonomous vehicle is to behave like a smart vehicle that is like, being piloted by human piloted, aircraft. What are autonomous systems? That is something people think they know, but quite clearly not really fully understood yet. And of course, we also have to think about systems engineering. Systems engineering is a very traditional, historically well-known field over a long time. Most of you are probably much better experts at systems engineering than I am, but we have been using it. But we have come up with some, let's say, stumbling blocks, and we had to sort of deal with them. And that's some of the things I'm going to talk about. Because we have to sort of basically incorporate things like models. Models are very, very fundamental to aerospace. Without a model, you can't move forward. It's actually, aerospace is model-based engineering. And we work with models of different kinds. You'll be quite surprised at the kinds of variety that we have to face. And I'm basically involved in teaching simulation. And basically one of the big confusing points is our models are not just diagrammatic. There's something more inside the diagram. And that's something that has to be understood, which is not really fully appreciated. So that's what that has to be sort of integrated with the regular idea of systems engineering. And this is really part of what we have to do while we continue with what, things like designing an electric aircraft or an autonomous aircraft and so on. Traditional systems engineering concepts are many, which are well known to all of you. Basically, requirements start with requirements. And of course, definition of the requirements is the starting point. And of course, there's validation, verification, and there's coordination across all the disciplines. And that's very important. Understanding the role of the systems engineer and the SE processes. And of course, if something goes wrong, being able to trace the fault, traceability. And in the end, yes, traditional systems engineering is very document-based, different kinds of documents, but document-based. And now we are talking about model-based systems engineering, which is essentially trying to incorporate modeling. And again, here's where I caution people. When we say modeling, it is not simply diagrammatic models. It is each of those diagrams are just sort of representative. Inside that, there's a lot more. Dynamic systems, automatic control systems, optimization, autonomous planning and control. And this is where the problem comes. Autonomous planning and control, although it seems like an automatic control system, it is completely different. And this is where one has to be sort of very, very careful. So what is the big issue in model-based? And the whole idea, as I mentioned already, is we want to integrate proven system models into systems engineering and make it very model-centric. Model-centric approach rather than something that is much more traditional. And of course, this means the models have to go into verification and validation into all the traditional areas of, starting with the requirements and going right to the end. And I'll explain some of these varieties of models, which are quite, new to most of the engineers. They are needed because of the kind of problems that we are dealing with, ultimately bearing on safety. Aerospace is still one of the world's most safest modes of travel. And we, are definitely committed to the ideal. We will continue with that approach. Now, start with autonomous systems. What are autonomous systems? And they arise mainly because of the synergy between interacting subsystems. I learned this long time ago when I was a youngster. I grew up in Bangalore in India, and basically my father was an engineer too, and he basically taught me this idea: 2 + 2 is 5, and it is very, very important. And I can tell you the best example I can give you is the mobile phone. If I take out all the parts of a mobile phone, I ask you to put it back together, unless you're an expert at putting it back together, it'll be very difficult. It needs a special kind of integration. And that is key. This is where synergy comes in. This is where now systems engineering, on the other hand, involves decomposing a process into system decomposition, into subsystems. So can we make one the inverse of the other? And if we can do that, we fully can sort of design autonomous systems. This is where it is very useful. So, but autonomous systems with control are not the same thing as automatic control systems. Automatic control systems usually work almost instantaneously on the same timescales, whereas different timescales are involved in autonomous systems, and it's a lot more complex. And they are, of course, aerial, aerospace, marine vehicles, other autonomous systems, which are, robotics. I also teach a course on robotics. So basically, there are autonomous systems in various fields, and the basic principles are the same. Now, looking at it from a systems perspective, one of the main issues that we have to worry about is dependability, trustworthiness. And basically, there are many parameters, primary ones: safety, availability, reliability, and security. Very, very important. We will never sacrifice safety at any stage. Dependability is absolutely vital, especially for all these electric vehicles and so on. And it should be suitable for future systems. This is very, very important, future systems. Now, interconnected dynamic systems, basically to understand what we mean by modeling, there is so much that goes into the model. There's the algebraic, the geometric, and the hierarchical aspect of these various models. There's the block diagram, which is what you see, which comes from signal flow graphs. But inside, there's basically a model which, Simulink, for example, it's not a diagram tool. Basically, it's a differential equation solver, and it's not something that is actually only diagrammatic. Much more in terms of connectivity properties and so on. So basically, this is what facilitates the decoupling and decomposition, and this is very, very important. Now, going further, the first step, if you're looking at it from a systems engineering process, you have to start with setting up the requirements. And of course, I'm sure most of you are aware of that. That's really not the main reason why I'm talking about it. But the point I'm trying to make here is that while doing all this, thinking in terms of the models and including them right from the start is very fundamental. It is absolutely important. If you're looking at, for example, a UAV, think of all the aspects of it. How do you launch? How is it controlled? We say autonomous vehicles. In the end, nothing is totally autonomous. There is a ground controller somewhere, and he has overriding, responsibilities. He can sort of do things which are quite significant. So yes, they are autonomous to a large extent over a certain time scale, but if you think of it as forever, no, they're never forever autonomous. And of course, in terms of the role of the systems engineering team, very important to understand there's a team. It's usually not a single person. There's a team of systems engineers who are actually acting as referees and bringing together people of different disciplines. And this is very important, making sure all the requirements are met and the customer's expectations are sort of satisfied. And of course, the other important point is, decomposition of the system itself. And I'm afraid to use the word block diagram. Rather than using block diagram, I say diagrammatic approach, because the diagrams these days are much more sophisticated. They have a lot more meaning, various tools, various types of diagrams, and these have to be sort of dealt with because they have a lot of physical meaning. Sometimes you switch between a block diagram, a systems, circuit diagram, VHDL. There are a lot of switching of operations that happen, and all that we have to deal with. So that is part of it. And so it's not just a block diagram, but this is where the multidisciplinary diagrammatic model-based representation comes in. And this is where the systems engineers have to sort of be able to sort of deal with these multidisciplinary fields and deal with these various kinds of diagrams. And basically, if you go back to you're not actually saying that we're getting rid of traditional systems. No, that's not at all the case. So the diagrammatic approach and is basically there. The documentary approach is there, but this goes a bit further. And so there must be a link between the model-based multidisciplinary approach and the traditional systems engineering. And this is where the diagrammatic representations are very important. They go into the documents, and that is, but they're not, it's not an end-all situation. And the next step, of course, air vehicle integration and test. We don't ourselves do a lot of this, but some of our client companies do it. You know, they are involved in some of these things, and they come and talk to us about various aspects, and whatever help they need, we are willing to provide them. So basically, there are key steps: studying the options, trade-off studies, implementation, and looking at the goals. And in the end, there are, towards the end, once there are requests for proposals and a lot of negotiation, there are surprises that come up. And of course, the most important thing is performance and cost. You want the maximum best performance at the lowest cost. Most of the time, some of the people who come and talk to us want some of these services done for them free of cost, simply because they can't afford it. And we understand that problem. It's been particularly bad over the last 2 years, thanks to the pandemic, because the airline industry has suffered enormously because of that. So one of the things that happens is the requirements keep changing, and we have to sort of scrub the old designs, replace them, quickly change it, put it into the format that is acceptable. And of course, in the end, you come up with an acceptable design. And modifying the requirements, you know, for whoever the customer or whatever, that has to happen quite quickly over a finite time, and you keep sort of updating your process. Now, the point here is I now come to this final reviews point, and here you don't actually when I say final review, you don't actually come up with the final review. That's starting point for the preliminary design review. And then, of course, then there's a lot of optimization that goes on, a tremendous amount. Optimization is a whole process. At one time, it was considered to be something that you do optional, but now it's not like that. It is absolutely required, and you optimize the plans, you optimize almost every aspect of the design. And this is quite a repetitive process. You may have to go through many of the systems engineering processes again and again. It involves tremendous repetition and repeat. And this is why we advise people never to do things simply on paper. Everything has to be done in the computer. So you can use, computers are very good at repeating things. So that's very important. Once the design is completely optimized, then we have the critical design review. Basically, we are there, and at that stage, the final set of processes are sort of implemented, and we come up with a final design. So I've actually rushed through this whole thing. I mean, normally this is something that we cover over a huge course for several of our participants who come from industry and so on. But I've rushed through the whole process very quickly. But, there are several points, but there's the main message here: continuously being able to incorporate new models into the systems engineering process. When I say new models, we get new models coming up all the time. I have learned a lot of new modeling techniques over the last few years, something that I never knew at one time. So it continuously happens: dynamics, control systems, autonomous control systems, all kinds of planning tools. So there are new models coming up every time, and it's amazing. Actually, in the end, they produce the goods. So they have to be integrated into the whole systems engineering process. I know there's a lot of resistance from the more traditional people, but they learn to do it, and they are doing it. Several of our students work now with systems engineers, and they routinely use things like Simulink and VHDL and other tools as well, and which are regularly integrated. But then there are newer methods coming up, and that's the point I want to make. There are newer, I don't want to elaborate on it because then I'll be going into a separate talk on autonomous systems, which is by itself a huge area. But that's what is the need of the hour. Right, I'm done there, and I'm open for questions. I'm sorry, I apologize if I've exceeded the time by a few minutes, but I'm happy to take questions. can I put this on non-systems mode so that, right. That would be more easy to sort of answer questions. Is there any questions from anybody?
So thank you so much, Dr. Vepa, sir. So for this session, actually, we have not received any questions.
But I'm happy. Any questions? I'm happy to answer. Only if it's something to do with specific aircraft, I may not be able to answer because we won't reveal some of our customer data. So, well, I wouldn't call them customer. They're basically talking to us.
So yeah, we have one question received. So yeah, so how do you see the bridges will be developed between domain independent multidisciplinary models and domain specific or concern specific models that are generally used for optimization?
Well, if you look very closely at the optimization tools, they are tending to be more and more not domain specific. I mean, these tools are, so it's a matter of learning. This is where we have to learn some of these, using these tools and reinterpreting them, making them across. And people are learning. And it's just like control systems, for example, just to give you an example, although it was, it began as an electrical subject, now control systems are not considered to be electrical or electronic. If you can use control systems in various areas, various ways, it's completely domain independent. And that is exactly what has happened to optimization as well. All the tools can be used across various domains, and that is already happening. I don't know if that answers your question, but these subjects no longer are restricted to one small area. It is not, for example, like structural optimization. When I learned optimization, I learned it as structural optimization. No longer true. Optimization is much more wider now. Okay, it's not domain specific anymore. Does that answer your question, or?
Yeah, so we have a yes, that answers these questions very perfectly. Now we'll have another question for you, Dr. Vepa. So you have mentioned about the requirements getting changed due to schedule. How is MBSE and project management getting along in current times?
Well, MBSE, actually, there's a lot of the traditional systems engineers who sort of work with us. They are not happy with having to deal with the right variety of models. But what we do, we bring in the experts in that particular field. Although, I mean, I teach a lot of Simulink modeling, but in the end, the industry guys are much greater experts than I am. And they come up with huge Simulink models. So they have to talk to each other. That's the only way in which you can get across these barriers. So communication is the way out. All right. So basically, the systems engineering expert and the Simulink expert has to talk. And this is how they break those barriers. And the systems engineers have a bigger role because they communicate across. They go across to other people and talk to them. So they have a big job. They have to understand these guys. They have to understand the other guys as well. So this is a much bigger, problem. But they get over it. So that's why we train. That's why we recommend that some of these guys are trained in, with an understanding of what the other chap is doing as well. That is the only way we can get across these barriers. But we are getting across those barriers because we do work with people. I personally, I teach a course in Simulink and simulation, and most of my students get employed in a simulator company. And so basically they become experts. They are 10 times more experts than me, although they may have learned their originals from me because they are actually on the job for years and years. And basically they communicate with the systems engineers. And they also have, because they have a broad knowledge of both these subjects, that communication is feasible. That's the only way. You have to understand the language of both sides.
Okay, so we have many questions coming up for you, Dr. Vepa. So another question. So how do we integrate safety and security, including data security, into MBSE?
Well, security and safety. Safety is the starting point. You may have observed in one of my slides, I used the word proven. And I underlined it. It's very easy to say, but a lot goes into that before you get to the stage of using some of these methods. And and the main thing is documentation. You document them. That's very important. So you use only proven methods. I can give you an example. You may have noticed on all these Mars programs, the United States has been exceptionally successful with some of their rovers, whereas some of the other countries have not been that successful. I know one European organization that tried to launch a rover and it wasn't very successful. Why is it? And it turns out you've got to give the Americans the credit. What they do is they go slightly proven technology, so they can step back a little bit rather than going for the most advanced, which is a wrong thing to do. I mean, many years ago, I heard a talk from someone. He said, don't combine two new things together because the probability of something going wrong just goes up. So you step back a little bit, use proven technology, and it turns out you'll be very successful. So you just have to step slightly back and make sure that you're using proven methods but you will still get a fairly advanced system. It's just that you're stepping back a little bit rather than using the most advanced method. So that little bit of stepping back is very useful, and that is where the the difference lies. And that, of course, comes with experience. Now, of course, people here have mastered it as well. Okay, that answer your question?
Definitely, Dr. Vepa. So we will take one more question and then we will move to the next talk. Okay. So how will the DO 178 BC and DO 258 standards evolve themselves to accommodate the MBSE based development?
Well, that's something that is difficult to predict, but I think to a large extent, all these changes in the standards will come up as the usage of the methods is becomes more and more prevalent in the industry. I mean, most of the work that I do with some of the aircraft industry is with the Future Systems Group, and they are looking so far ahead. So it's kind of difficult to predict how to some extent, they don't worry at this stage about standards because they know that by the time they're ready to implement some of these things, all the standards will be different and they will be there. They can implement it, meeting all the requirements at that time. So right now they're looking very far ahead because if they don't plan ahead, as I mentioned, the Concorde, most people don't know this, it actually started in 1949. I have papers that were published in 1953 with block diagrams of what was being planned for the Concorde. 1953, and it took about 24 years before the Concorde actually flew, and it flew for 27 years, and everything came to an end in the year 2000. So, that shows that it takes a long time before an aircraft comes off the rolls out of the hangar, completely ready to fly. And I know that such aircraft are being designed, just like the same story with motor cars. Electric vehicles are being going to come out in a huge way in the future. So just like that, the same thing is happening with the aircraft industry. It's just that we don't see it so easily right now, but it's going to happen. So the standards will evolve as they are sort of used. Right now, some of those standards are set aside, and because if you stick with all the standards as they stand, you won't be able to develop some of these new systems. So basically, as they use them and as they sort of apply them, they have to modify the standards according to the use. So the use cases are very, very important.
Okay.
All right. If that's a fair answer.
Yes, definitely. It's completely answers my question.
Many years ago, actually, I trained as a lead assessor for ISO 9. That was about 20, 30 years ago. Lead, 9001. But we couldn't do much with it. We had to set it aside because if you're looking at future systems, sometimes you're thinking so far ahead. Actually, I wasn't thinking so far ahead. I was sort of made to realize that you have to do that if you're looking at aircraft projects, because they think 25 years in advance. Already the legal framework for future cars has already been defined by the UK government. So if they talk about 2040, 2050, so we have to be prepared for that as well. Same thing with aircraft. The emission standards have to be met. They are there. They have to be met. That's it. That's the law. Okay.
Okay. Thank you so much, Dr. Vepa, for sharing your insights. I mean, this is really very helpful, and this is really fascinating to hear such good intellect and, such, I mean, I cannot tell you, I mean, how inspiring and how knowledgeable it is. So thank you so much.
Thank you. Thank you very much. Thank you. Thank you.
Thank you. Again, Dr. Vepa, I would like to thank you for this insightful talk on the MBSC and aerospace application perspective.
Okay, thank you. Thank you.
Now, for the talk fourth, I would like to invite Dr. Manju Nanda ma'am, serving Chief Scientist at National Aerospace Laboratories. She is serving for 26 plus years for service for CSIR, delivering significant impact in the field for safety critical systems for aerospace applications. We welcome you, ma'am.
Thank you. So I'll first try to share the screen and then continue with my talk.
Sure.
So let me know if you can see the screen.
Yeah, it's up, ma'am.
Okay, yeah. 1 minute. Is it in the slideshow?
No, not there.
Not yet?
No,
Not yet.
no, ma'am.
Yeah, fine. So let me know when it goes into the slideshow mode. Okay, yeah. It's okay? Yeah. Yeah.
Yeah, perfect.
Yeah, okay. Thank you. So first of all, hello everyone. I am Dr. Manju Nanda. I am Chief Scientist in the National Aerospace Laboratories, which is a premium organization under Council of Scientific and Industrial Research. So just to give you a background, so I would first of all like to thank Director CSI NAL, Jadhav sir, PGD Civil Aviation Program, Dr. Pashulkar sir, and Inkose MBC India, who actually proposed my name to give this talk. And of course, my team, without whom I can hear some crosstalk. So request to
Can you mute yourself?
yeah. And my team here who has helped me to realize the MBSC, what we have implemented in NAL. Shall I move ahead? Because there was some crosstalk happening. So just let me know.
Yeah, please go ahead. I think it is stopped now.
Yeah. So I come from an organization which has a mandate of development of national strengths in aerospace sciences and technologies, where aerospace software is a major thing which they focus, because a lot of indigenous development happens in our organization. And it is in this ecosystem where we initiated and implemented the MBSC for the flight software. So today I'm going to share that story which we have done successfully, and it's just a baby step we have reached to implementing, but there's a lot to achieve. So what they talk about safety critical, there are these some of the jargons you keep listening from people is a safety critical system is expect what is expected and not what is not expected. Very obvious. Then earlier when we started our career, they said take the requirements in black and white in the textual format. So when graphics started coming, they said no, graphic is something, seeing is believing. So these are the jargons which were passed on to us, to a software developer, saying that you're going to develop a safety critical system. Now today when we are shifting to a new paradigm, what I feel is when I'm speaking in front of you, I'm going to tell what I have experienced. I will believe. I will not believe in what people are writing in black and white, or what people are saying is capable. There is a capability of this. You can achieve this. You can achieve that. Because I feel if you experience, you can basically tell, yes, it is for sure. So today I'm going to share the story of MBSC implemented in NAL, because we have experienced it. We're going to talk about the experiences, what we have about MBSC and how we went forward, and how is the future plan for MBSC in CSIR NAL. So this is a reference from Inkose.org, which the earlier speaker also flashed it. So there are a lot of MBSC claims. It reduces human error. It has a faster turnaround in case there is a requirement changed. It improves the technical communications because there's a structured way of communication. It reduces design and execution risk. Auto generation of reports directly from the system design, traceability from the requirements. Then it bridges the gap between the system domain, hardware domain, and software domain. This is what they talk about, the intercommunication between the systems, where you talk about system of systems and system integration. Now, my focus would be basically what we achieved in carrying out the MBSC at NAL will be the requirements capture, verification, validation, integration, and software, of course. And when I talk about integration, verification, validation, it will be at various levels. One at the software level, one at the hardware level too. And what is claimed on the left-hand side, I will say whether you should believe in these facts or what MBSC is proposing, or you should believe it with caution or believe it blindly. So that is what I'm going to talk about. So how was our journey? So it's a story about the hare and the tortoise, where it was a slow and steady. So today I can say that, yes, we took baby steps, and then we did a slow, gradual transition from a conventional document-centric software development lifecycle to a model-based software development lifecycle, which is highly tool-based. So in case of the software group at NAL, we did a slow migration, which was no automation, where we use the conventional SDLC, to partial automation. And then we have also achieved a more automation kind of a thing, where it is mostly tools and the tools are integrated to do a seamless transition. A lot of speakers did speak about the seamless transition happening, which is the need of the hour. We did it only for our projects, so I cannot claim for other organizations, but at NAL level, yes, we have done to some level of seamless transitions between the tools which we are using for our model-based applications. So this has been a paradigm shift. So in the SDLC, there is a keyword called as paradigm shift. So you talk about the paradigm shift from a conventional document-centric SDLC to the model-based, and there is a new concept called as formal method. So at NAL, we have also started working on formal methods, and we have our own knowledge database where we are trying to use it for our future applications. So something we can be very proud of is something of the first in the software engineering for the civil aerospace. So if you see the chronological order of the RTCA DO 178B, people who are coming from the aerospace background, they actually know what DO 178B. I will not dwell upon that. So it was first introduced in the year 1992 till 2012. So what NAL was doing during that time? So what we did is we actually established the complete SDLC process for our indigenous stall warning aircraft interface computer system for the PT-1 aircraft. And this was during the year 2000 to 2004. So that was a design assurance level A, which is the highest criticality level, which was successfully completed. Apart from that, during this time, we also did this RS Autopilot. The time is from 2006 to 2011. The DAL level was A. ECAS is the engine instrument and crew alerting system, which was designed, developed, and went for the certification from 2009 to 2012. And then the enhanced fatigue meter for the Jaguars in the year 2003 to 2006, and the advanced one between 2009 to 2013. But this was of level D. So this was a time when we were the pioneers in establish the entire SDLC process adhering to DO 178B. During that time, there was a realization in the aerospace industry all over the world that new techniques are being introduced, and these new techniques are going to make my software robust. It's going to give me more power to ensure that I basically deliver a safe software which is functionally competent as per the requirement and also performs as per the top level requirement. So in Jan 2012 was DO 178C was introduced. During those days, what NAL did is after implementing these, we also did some kind of a pilot study projects, which was basically to use formal methods for safety critical application. The work was carried out in the year 2011 and 2014. What was the outcome? We have built a very strong knowledge base at NAL where we know whether to use a formal method for a particular application or not, what is the kind of effort required. So we have the knowledge base at NAL. Then we did a model-based software engineering pilot project on a known product to ensure that when we transit or go from a document-centric to the model-centric, what are the advantages, what are the disadvantages? Because the world is going towards model-based systems engineering. Is there a need to go? If yes, I should be able to quantify what are the things required to do so. Then at NAL, similar to Bosch, we have also developed an integrated formal model-based framework where we basically have a framework which has a capability of taking conventional approaches, model-based approaches, and formal approaches to give me an end-to-end from concept to certification kind of a approach implementation based on the project needs and the requirements. And there are industry standards, and coming from an aerospace, for us, it is DO 178C where we have to adhere to. So anything we do in-house always has to adhere to DO 178B. DO 178C is something which I have already spoken. It talks about model-based guidelines, tool guidelines, object-oriented guidelines, and also formal method guidelines, which come as a part of DO 330, 331, 332, and 333. So what was a pilot project? So what we did at NAL was a proven system of stall warning. We basically translated the entire stall warning system for a model based. Now let me give you a point of caution. Nothing is completely model based. Model based is never 100%. It is 60 to 70%. 30% is still a manual effort which you have to carry out. But it definitely improves, or it helps us in improving the complete flow and automating. So then we basically, what tools would be used was, we used the Simulink State Flow and the embedded coder. and the complete functionality of the core algorithm, which was the basic brain for the system, was modeled. Autocode was generated. The code was tested compared with the conventional thing, and we basically adhere to the model guidelines as given by MAP. Similar to a conventional manual coding where we have the coding guidelines, in case of model-based, we have to adhere to the model guidelines. So in this case, we adhere to the MAP standards and generated some metrics to prove that, yes, it has an advantage, and if case required, if the system is complex, it is advisable. If it is a simplistic system, you need not go for model-based. You can go with a simple approach and implement it. So this was basically was the takeaway from this proven thing, that the code analysis and design time was cut in half, integrated the complete workflow, and we realized that the readability, reliability of the auto code was better than compared to a manual coding, because you have various people of different experiences who do the coding. So in case of model, once you have frozen the model and used the model guidelines, the auto code becomes uniform. So that was the advantage. Then moving ahead, what we did was we generated various metrics to ensure that what, in case in future projects, if we embrace model-based software engineering, will that help us? As part of that, we generated various metrics, something like the tool analysis metrics, applicability metrics, process requirement analysis metrics, process design analysis metrics, process test metrics, and process code metrics. So if you see in a typical SDLC process, these are the various phases from the requirement to implementation to the testing. We wanted to make sure with the approach of model based, it basically gives me an advantage in each phase of the SDLC process. So just giving you a kind of a highlighter or a kind of a feeler, what is the thing? So if you see, there was a quantitative, I could quantify the model based thing, saying that there was an advantage of using a model based approach as compared to the conventional approach. So this was the requirement analysis metrics where there was an improvement. And this was a metrics where I used a single tool or integrated tool, because for a given process in SDLC, a single tool does not give me the complete solution. So we had to use a combination of tools to implement an effective SDLC in case we were suppose we were to adopt the model-based approach. So this is the metrics what we generated. This is in case of the testing of the autocode. We did do the autocode testing because most of the tool vendors say when you do autocode, you don't have to test it. But we wanted to make sure that the coverage what I get at the code level, I get the same coverage at the autocode level, and that I mapped it with the model level coverages. And this is the code metrics. So the autocode did have an advantage. The only thing was some places the size of the code was more than what was in the manual code, because the kind of, if you take an experienced person's coding, his code footprint would be smaller than the autocode. So that was the difference. But definitely the advantage was, regeneration of the code. Once I tweak the model and regenerate the code and then get it for clearance was faster compared to a manual level. So after realizing the advantage of model-based, we then went through a systematic approach for implementation and adhering to DO-178C and 331. So 331 is model guidelines. So what we did was we first established an environment where the flight-worthy code was generated for a in-house indigenous display computer, and the same code was integrated to the simulator. So in case of the life cycle of a flight software, you develop the code, you test it in the rig, you many times test it onto the simulator to give to a feeler to the pilot how the system is behaving, and then you go to the aircraft. So the first task was to establish an ecosystem and environment to generate a flight-worthy code which could go to the target as well as to the simulator. Then we went ahead and designed and developed an integrated avionics display processing software with the certifiable capability and adhering to DO-178C and DO 331. So the software application what we generated was capable of generating the primary flight display, navigation and ECAS application and the complete logic. And we generated all the artifacts which was to be submitted for the certification, but this was a proof of technology. So we didn't go to the level of certification. Then with the application already available, there was a need for modifying this application for a synthetic vision, where we again integrated with the simulator. What we realized is because we went for a model base, the tweaking and the changing from one application and adding some more information and developing another application with model base, it basically had an advantage. Had it been a basic document and manual coding, it would have taken months of time. In this case, we could complete it in a month's time. So that was the advantage. Then what we were told to develop the first indigenous brake management system software for the PT1N, which was a proof of technology. In this case, we went through the complete cycle of model based and then also cleared at the organization level for integration onto the aircraft. So this was the proof that the model based application software could be integrated onto the aircraft, demonstrated the functionality, and we also carried out the basic test like the engine runs and the low speed taxiing test. So that was the kind of a systematic approach from 1 to 4, where it gives us the confidence that yes, if you use model base, it has a lot of advantages. So this is the complete environment or the block diagram of what we did it for developing the environment. If you see, this was the complete model-based environment. And when we generated the auto code, we could put it to the simulator and the same thing could be ported to the embedded target. And this is how the flight displays where application was running. Now, this is something we have actually implemented in the NAL, and very proud to say that we have integrated the entire V model, which adheres to DO 178B standards. And apart from that, DO 331, because we are using model-based approach. And the catch here is if you're going for model-based, there are going to be a lot of tools. And for the certification, we have to go for tool qualification. So that process and that knowledge base also we have developed, and we will be going for the future projects for the tool qualification adherence also. Now, starting from the planning phase, the plan documents, they were captured, were textual entry, and then it was DOS where we captured all the documentation and the requirements. Then came the requirement phase where we used the Rhapsody and SCADE system architecture using the SysML. Then the design phase where the UML guidelines were used. And the advantage of model-based was these tools gave us the capability of generating the modeling documents. And then we had to integrate it with our other documentation and give proper links. So that was the effort saved and the ease of migration from a requirement change. So in case there was a requirement change in the model, I would change and then regenerate the document. So the regeneration of the document became automatic rather than, manual entry, verifying, reviewing. So in this case, what you see, you actually got it into the document. So that was the ease. Then we did the implementation. We did the, at the same time, if you see the V model where the designs were done, we did the model designs. So we ensured that the model which has been captured, which will be generating the auto code, we did the model-based testing. So we had the model-based test coverage. And then when we did the code level testing, we did the code level testing and generated the translation from the model to code to ensure that the model does not introduce any extra code, because in case of embedded flight softwares, the footprint of the code size is very important. So that we had to make sure, otherwise the effort of embracing model-based engineering for a flight software loses its charm, because if the footprint is big, it basically does not help us long way, because any of the flight software life is for around 10 to 15 years and it undergoes a lot of requirement change and upgrades in the software. Then the requirements, we developed the requirement based test scenario for the rig, which was done manually. and then finally aircraft rate. So in this V model, 60% was done using the model-based tools and automation. The other 40%, whatever you say, you cannot automate these things because these are very, very project specific, target specific, and the rigs cannot be automated to that level because these are complex systems and I cannot do everything using the model-based techniques. In order to prove the efficacy of the model base, we basically did the mapping of the model base coverages to the code level and to the hardware software integration test coverage. So this was something which was asked by the people who wanted to give us a clearance for model based approach for our future projects. Then the requirement change impact timeline. What we realize is if I change a requirement, the re-verification, the requirement change to the model change to auto code change to re-verification timeline. If I have to do manually, there was definitely a reduction in the timeline. Then the best part of model base was visualization of what you are going to implement. Now, since any systems engineering is a multi-domain people come, the textual interpretation of the requirement is different by different people. It is like the blind people and the elephant. Their perception of the various parts of the elephant is different. Now, in case of model base, when you see the model, everybody thinks in the same way. So that is what advantage we found was good. So if you say this is the requirement and you show the model, everybody would align to the same thought rather than reading the textual and interpreting differently. So that was the biggest advantage I found it at when we were implementing the model-based approach. Now, to prove that what we have done has actually worked, I'll just show you some videos. So the first video basically is, so on the right hand side is the simulator and the left hand side is the symbology which we generated, and the data is basically running through a flight model, and we see the data which is, and the displays are COTS proven, and this is what was indigenously developed. So we realized and we proved it that what was done in-house using model based, it is as the functionality and the performance is at par with the COTS one.
Sorry, ma'am, we see your slide.
Oh, you can't see the video? Okay, not possible. Okay, sorry. Can you see the video now?
No, Dr. Manju.
I don't know. I'll just see.
Do you have two screens or something?
What do we have to do?
Stop sharing.
Wait. I don't have the thing of stop sharing. 1 minute. Did I stop? Wait a minute. I'll just do that.
Yeah, now you can share the whole screen. Is the video coming in as a separate?
No, it's embedded actually. I tried it in the place, so.
Okay. Try again.
Yeah, I'm trying to share. Can you?
We can see the PPT now.
Okay, but I have to share it and it's not got into this.
I think you have to first stop sharing the current screen.
I did share that. I did do that, sir. Yeah.
Okay.
Yoga?
Yeah.
Sudarshan, she's using multiple monitors.
I have a feeling she's using multiple windows. Yes.
Yeah. So probably the video is going to the other monitor.
Okay. Okay. 1 minute. I'll just.
You could either duplicate the screen or.
It doesn't have an audio.
Yeah.
Okay, is it? It's going, sir. I don't know.
Now sharing is not there.
Okay, sorry.
We can see your whole screen now. Your
Yeah,
desktop.
so I'll have
Yeah.
to do that. So 1 minute. I will. Okay, what I do is
Maybe
I'll
just
stop
open
share.
up the video separately. Yeah.
Yeah.
That is possible. Yeah.
No, I done it in the. Okay, I'm sorry for the discomfort. Yeah, I stopped sharing. No, I stopped sharing. So 1 minute. I'll just do that because I have screen. So I think that would be the problem. So I'll just. Is my screen visible, sir?
Yeah, we can see your PPT.
Okay, so I have to go.
We can, yeah.
I hope it.
Now it is the dual screen thing. You're
Yeah.
seeing both of them.
So can you see now?
Yeah, perfect.
Yeah.
We can see.
This is a video where on the right hand side you have the actual display, and on the left side is what was done indigenously. And what we did is from the flight model, we actually generated the data and to prove the performance and the functionality. So if you see the dials and all, and the performance was actually matching. And this we ran for a hour's time to show that the in-house model-based approach for the display, what we implemented is actually working perfectly fine. So this is just to prove that the complete model-based thing, what we did was effective. Now, this other story, what I told was there was a modification in the display where this is basically an enhanced synthetic vision system, which I do not know how many of you know. So this basically was the system setup. I'll just go a bit faster and I'll show you exactly what we did. So if you see on the left-hand side was the actual IADC display, and we remodeled and made the ESVS application because that was the need for the ESVS application to be mounted for the to the HUD. And to the extreme right, we have the simulator data running. So this is my system. This is the modified system. This is again done using a model-based approach. So this was to prove that the existing symbology, if you do the modification run, and this time taken was really less. Had I had to do a complete manual thing, it would have taken really months together to prove and test it at the various stages in a typical V model. So this again, this is a landing thing. So if you see on the left-hand side is the PFD, and on the right-hand side, you have the same simulator. So this was to prove the efficacy. This is just some system definition. And finally, it is in the simulator. So in this case, all the displays are done using the model-based thing. And this is my ECAS. That's my ESVS. And this is a PFD. So this basically showed that in case of a model based, we basically developed an environment. We proved the efficacy of the model based ported onto by system realization. We did the demonstration. The best demonstration was basically comparing it, benchmarking with the already COTS proven systems, and then integrating with the simulator. So that was the approach what we had taken. Now, any system is basically either data intensive, logic intensive. It could be an open loop system, closed loop system. And then you have another factor called the criticality level of the system. Now, most of the model-based thing, what we have done was a data intensive system where the demonstrations or the videos I have shown. The other was the control intensive system where we went ahead and tested it on the aircraft. That was the brake management system. I do not have much of the videos and all because it's highly proprietary, but we were successful in taking the requirements, doing a model-based design, generating the auto code, testing it, porting onto the target, getting the basic clearance for the ground aircraft integration and LSTT. What were the learnings? It basically, what we realized with model-based is lot of logic corrections can be visually seen and analyzed because you see and you can say, yeah, there's a logic problem and all those things. Then we can do a performance analysis, not runtime in the simulator. We could do that. It is it was not actually running on the real-time thing, which can be done on the model level. We know that if I have given a timer clock of 1 second, it basically has to do a transition. In a conventional way, the person who is analyzing or testing should have that kind of an experience. Of course, in case of model-based also you need to have, but if you show and simulate, you know what you're simulating actually is translated to the auto code. Now there's a common platform of understanding and visualization amongst the various system domain people. Software are not domain experts. So in order for us to develop a slide software, we usually get the system domain people, take the requirements and implementation. System domain people give the requirements. The realization is the responsibility of the software guys. And in case we fail to capture those requirements properly, we basically do not do justice to the system which we are clearing. So that's why model-based actually helps us in understanding and visualization at the same level. The model testing mapping from the top level requirements can be done and the errors can be captured early in the life cycle rather than the code level or target level. This we have realized many times the requirements when it translated to the model, we could capture it at the model level itself and we did not go ahead with the auto code generation. We could reuse the same model by a little bit of tweaking. We could reuse. I showed you the example of the IIDC application and the ESVS modification. Ease of documentation leading to an ease of impact change process. So what was the documentation? In case there's a logic correction, it would be done at the model level. See, the tools themselves provide the capability of generating a document. Now, what is impact analysis? Now, in case of the safety critical system, in case there's a requirement change or there's a design change, the first thing the designer does is to carry out the impact analysis and to project that these are the changes, this is the timeline, and this is what I will need to do a kind of a rework and recertification. So basically, it was an ease of change to implement and the turnaround time was less. So that was some of the learnings when we carried out these projects. So re-verification of the claims, what was done, it reduces human error.
Hello.
And yes, sir.
Sorry to interrupt you, ma'am. You have left with 1 minute.
That's okay, fine. So I just wanted to say these, what was claimed earlier, it is true, but there is still some manual effort is required. It is not completely automated. So that is the hard fact and you should go accept that and move ahead. What are the pros? So effective software development lifecycle, model capture of logic intensive requirements for ease of understanding, capturing the design flaws early in the life cycle, especially related to functionality, timing, especially not real time because you are not porting onto the target, and safety for the functional safety. Reduced change requirement implementation, the complete turnaround time gets reduced, better visualization, and it has a long-term benefits of the initial hard work. So the initial hard work comes as a con. Model-based is never 100%. You have to learn new tools. That is the challenge. Many people who are comfortable in that tool, the migration from a tool to the other tool is a real challenge. Aligning and training the team for model-based software engineering. So this people have to leave the comfort zone because most of the colleges and all, they teach you coding and also that's the easiest way. But to align for the model base, you need to put in an effort. So there has to be a lead time if you want to adopt a model based kind of a framework or a process in your organization. Then you need additional documentation. So as I said, model base is never 100%. The additional manual thing you need to document. So that is something you need to do an extra thing. But once done, it becomes easier. Then some of the additional activities is you have to establish the environment, the tools which you're going to use for a particular project. And the biggest challenge is tool qualification. So tool qualification is the biggest thing. If you're doing for prototyping, ground-based, it's okay. But if you're going for an airborne system, tool qualification. And tool qualification, each tool is an SDLC process. There's a guidelines which tells you what are the artifacts you need to generate for tool qualification. Those are the cons. Now, based on the pros and the cons, we thought pros are more and we went ahead with the brake management system. So I will not be going ahead. These are the key features what we have used for the implementation of the brake management system, which actually was from the concept to the flight ground testing. And the way forward. So we are going ahead with a model-based approach for the FARAS Mark II application, which basically will be adhering to DO178C, DO330 and DO331 standards. And the computer will house multiple functionalities, which is the brake management, limited authority, automatic flight control system, stall warning protection, utility management system, and the environmental control system. So today at NAL, we have already embraced the model-based and we are going ahead for the new advanced system, which we are going to implement in-house indigenously for the SARAS Mark II project. Thank you.
Thank you, ma'am. What a wonderful journey you had.
Yeah, thank you.
I can feel that energy, and definitely it's not easy to have such a transition in org level. It's like everyone has to be very much aligned within a team to make this successful, and I can see that you have achieved that success. Wonderful.
Thank you.
Yeah. So okay, sorry, we are kind of ahead of time. So actually we had two questions. Give me a second. I just missed. Yeah. So we'll take one question in interest of time. So can you just tell us the improvement in metrics before and after implementation of model-based design achieved?
So metrics, I have already shared the metrics. There was a drastic improvement. So basically the capture of the requirement and the design, we realized the metrics is basically from the ease of tracing, ease of repeating the same activity and the document generation. So each of the phase, planning phase, I cannot use model based because it is more of a textual thing. In case of requirements, yes, it was an improvement. In case of the design phase, yes, there was an improvement. Autocode, yes, there was a drastic improvement because the manual coding was actually minimized. The only manual coding we did was anything which is connected to the hardware device drivers is what we manually coded. And at the other side of the V, where we did the model level testing, we could minimize the code level testing. So that was the advantage.
Definitely, yes. So with this, I would like to thank you for your insightful talk and involving us in your journey to transition to model-based software engineering for flight software. Thank you, ma'am.
Thank you.
Yeah. With this, we are done with our last talk for the day. I will invite Dr. Yogananda Jeppu, who is IEEE Secretary and also Fellow at Honeywell. Over to you, sir.
So this has been a great journey for us since morning. I think we have been at it from 9 a.m. today. So 9 a.m. to 11, we were talking to the students and the young engineers about systems engineering. And very happy to say we had about 100 odd participants and we had about 50 odd questions there on the chat. Some of them we could answer live, but some we have taken them down and we are answering them collectively. And these answers would be sent out to the participant. After that, we had a demonstration by Capella. It's an open source tool for system modeling. And we had a 2-hour session with the demonstration of the tool. We started the evening session with Dr. Kota's inaugural address, and he talked about LCA's 1 million lines of code to what it is going to be the future version of about 15 million lines of code. And he emphasized the only way to tackle this sort of a complexity is to have a digital environment. We had a talk from Dr. Sukant Bhatt, who gave a beautiful overview of systems engineering, starting with its history. And he talked about transdisciplinary subject and the nature of systems engineering, and how we start from requirements to use to retirement also. And he brought in a beautiful phrase that we are engineering a system, and that is something we all need to remember. And then he talked about barriers to learning and how we are told that we have to divide and conquer, but what we are doing is bringing together the components and bringing up a system. We had a talk by Mr. Niranjan from Bosch, and he spoke about the challenges of the various tools that are there, and Dr. Manju also talked about it from the practical point of view, that how many different tools are there, and we need to be working with all this. So Mr. Niranjan, he talked about Excel, DOTS, and the MATLAB, and how it is important to bring all these together and have a single source of truth. And that is the most important takeaway from his talk, that we need to have a single source of truth. And they have been working on this for quite some time now, and I think they have achieved it, but others who are listening in need to develop these things. We had a beautiful panel discussion on the future of the digital engineering, and some of the key takeaways for me personally was that 47% of the AI projects are just prototypes, so we have a long way to go there. And there was a beautifully presented material on the sensor fusion, the vertical and the breadth of it. So that was quite insightful. We had a look at the Capella tool that could help you bring in the systems modeling and put everything together. And then we had an example of an AR headset, and then using these digital techniques, how we can take more risk. I mean, that is a very insightful information for me, that you are taking larger risks, but then you are not eroding out the safety, right? So that is a good takeaway from the panel discussion. We had Dr. Weber, who talks about the MBSE as a very flexible approach, and he talked about synergy, 2 + 2 = 5. And then he talked about autonomous control is not the same as automatic control, and we need to remember this when we build systems, especially in the autonomous domain. And finally, Dr. Manju talked about experiencing the complete life cycle. And I'm very happy that she shared the metrics. Normally, people don't do that. And the experiences and the metrics, I think we could take it back to our companies and emphasize how model-based systems engineering can help us. Can somebody put in the tomorrow slide? So tomorrow morning, we have the SCP, that is early in the morning. We have the SCP mock test, and that is something I think a lot of people are looking forward to it. So I encourage people to register for that in case you're still there. And then we have the, it's too small for me. We have some interesting, talks on, leave it there, it's okay. Yeah, it's okay. It doesn't matter. I mean, people can see that. So we do have very similar structure. We will have talks in the beginning from 4:30 onwards, and then we will have a panel discussion on emphasis would be on medical systems, and then we have another few talks and then a wrap up. So look forward to have all the people with us again, and thank you so much for joining this summit, and thank you all the volunteers who have made this into a success. Have a good day, people from outside. Have a good morning and a good day.
Thank you everyone for making the first day of the summit such a success. Thank you, Yoga sir.
Thank you. Bye.
Bye.